We'll start in about 20 seconds.
Hello, everybody.
Okay, everyone, welcome back. We are going to do more antiderivatives today, right? And hopefully be able to finish the homework for 4.7. I assigned just the first part of the homework set, but there was some concepts that we hadn't discussed. So I want to just kind of take a moment to take a step back and look at when we were doing derivatives, we had this idea of higher order derivatives. So if we started with a function, let's say f of x, then we could always take its derivative, right? And we could get, f prime of x, which would be some new function, right? And there's nothing stopping us from going and taking the, derivative again and getting our second derivative. Now, when we did that, when we were talking about like optimization or curve sketching or shapes of graphs, the first and second derivatives were useful to us, right? I mean, they helped us figure out critical numbers, where things are going up and down, where we have concave up, concave down, things like that. But just generally speaking, if we start with the function f, we can take its first derivative, get something, second derivative, get something else, right? So now we have this concept of an antiderivative, which means that if I start, let's say, with the second derivative, I can go back by taking the antiderivative, right? And when I start here and go back, I'm going to get a new function, right? You take the, let's say we start at the second derivative, we go backwards, we should get the first derivative, but we have a problem. What's the problem? What was it about antiderivatives that we always had to include in our answers?
The plus c.
The plus c, which meant that this was a family of functions, right? A family of functions. So again, if you start with the function f and take its derivative, you only get one answer. If you take the derivative of that, you only get one answer. But if you start from here and you go backwards, you're going to get a family of answers. And so going back again, trying to go back here would be impossible to do because you actually have a family of functions that you would have to take the antiderivatives of. And each of those, each member of this family would have an antiderivative with another plus c, so to speak, right? Which would be a problem. So the question becomes, can we go backwards? And what is the minimum amount of information I would have to provide to you in order for you to go backwards? All right, so let's just do this with a problem. I'm just going to start with an example. Let's say that I tell you, let f double prime of x be equal to 2x. Okay, so I'm telling you that the second derivative of some function is this. And I'm going to tell you that f prime of 1 equals 6. And I'm going to tell you that f of 1 equals 5. And now I'm going to ask you to find f of x. Okay, so let's just try and visualize what we're being asked to do. We're starting here with the second derivative. And we're going to go backwards to find its antiderivative, right? Which will give us a family, right? This will give us a family. So when we go backwards, we're going to get this new function, which will be something plus c, right? So in order for us to figure out exactly which member of the family we're talking about, right? Because there's an infinite number of functions in that family. In order to figure out exactly which one I'm talking about, what I'm going to do is I'm going to provide you one piece of information about the derivative. So we start with the second derivative. We're going to go backwards to the first derivative. And then I'm telling you the value of the first derivative at a specific point. So here's a way we can kind of visualize this. What I'm doing is I'm giving you some function. This is not the function, but let's just say the red one is the function, the second derivative. Let's say the red one is the second derivative. When we do the antiderivative, we're going to get a family, right, of functions. We don't know which one it is, but I'm telling you that the family member that we're talking about has a specific point on it. See, I'm giving you some information about that family member, that point has to exist on it. So that narrows it down to exactly one function. And then you have it. And then from there, once we have that, oops. Once we use this, so we're now, after we do that, we're going to use that information and we will have the exact I'm going to say member, okay, member of the family. And then we're going to do it again. We're going to do the anti again. And that will give us the original function plus some constant, right? This will be equal to something plus some constant. Now I'm not going to use C again, because I don't want us to confuse C, have C in two places, so we'll probably use D. But again, this is going to be a family. And how are you going to narrow down which family member it is?
You gave us f of 1 is 5.
I gave you that f of 1 was 5. Okay? So we're going to do the problem. I just wanted you to kind of understand what we're doing. We're starting with the second derivative. We go backwards to the first derivative. We use some information, just one simple piece of information, just one point on the graph. That gives us the first derivative. Then we go back again, we get the original function. All right, let's do it. All right, here we go. So first thing we do, we start with this and we say, what's the antiderivative? Well, the antiderivative will be the first derivative because that's the second derivative. And what is the antiderivative of 2x? So use your rules.
X squared plus C.
X squared plus C, good. Okay, that's what we learned last class. So that's f prime, right? Start with the second derivative. Its antiderivative is this. Now we don't know what C is, but now we say this, but f prime of 1 must equal 6, which implies that when we plug 1 into this, right? When we plug 1 into the derivative, when we plug 1 in here and add C to it, which we don't know what C is, we should get 6. But that would mean that C has to be what?
5.
5. Right? Just subtract 1 from both sides, C is 5. So now we actually know it. We know that f prime of x is x squared plus 5. We've got the family member. Now we need to go back and do the antiderivative again, right? So we do the antiderivative. Maybe I should have labeled that. When we went from here, sorry, here to here, we did the antiderivative. Now we're doing it again. This should give us the original function. And that should be, all right, who's going to volunteer for this one?
I'll go.
Go ahead.
So antiderivative, that's going to be 1/3 of x cubed plus 5x. Plus C, plus C.
Plus C, but let's use D so we don't confuse it with the C we had earlier, okay?
Okay.
Plus capital D. So that's a D, everyone, not a 0. All right, but I told you that f of 1 was 5, right? F of 1 was 5. And that implies that when we plug 1 into this function, 1/3 times 1 cubed plus 5 times 1 plus D, that we must get 5. And you can solve this. This is 1/3 plus 5 plus d equals 5. And you can subtract the 5 and subtract the 1/3. You should get d is a negative 1/3. And now we know what this is. F of x equals 1/3 x cubed plus 5x minus 1/3. There you go. Any questions? Okay. We'll do another example in a minute, but I want to talk about something else now. So when we were doing derivatives earlier, right? I told you something. I said, let's say we have a function that gives you position. Okay, let's say you have a position function, all right? If you take the derivative of that, what does it give you?
Isn't it speed or is it acceleration?
Speed. Speed. It's the velocity function. And if we take the derivative of that, what do you get?
Acceleration?
Acceleration function.
All right.
Now that is a fundamental concept that you need to be aware of, especially if you're taking physics, because in physics you'll be doing a problem, you'll come up with a position function, and all of a sudden, well, the professor will be like, okay, so let's get its velocity function, and they take the derivative. And if you're not quite sure what's happening there, you're like, what the hell? You know, you need to understand that position derivative gets you velocity, derivative of velocity gets you acceleration. All right. So now that we have antiderivatives, if we start with the acceleration function, we can go backwards, right? And get the position. I'm sorry, we can start with the acceleration, we can go backwards and get the velocity, we can get the family, right? We can get the family. And then maybe if we can narrow down that single member, we could go back again and get the position. Right? Now that may seem like, okay, big deal, but think about what we're saying. If you tell me about an object's acceleration, okay? If you tell me the acceleration of an object at every point in time, what its acceleration is, I can actually tell you where it is at every point in time. But you need to be able to provide me just two pieces of information. Just tell me how fast it was going at one point and where it was at one point. Does that make sense? It's like, I need one piece of information about this.
So it's something similar to like the last problem, you need a value of some sort.
Exactly, exactly. In the previous
Overseas.
problem, we said, if we start here with the second derivative and go backwards, we can get the family. And to nail the family down, to get the member we're talking about, you just had to give me one point, one piece of information, right? And then from there, I could go backwards and get the position, family. And if you just tell me one thing about the position function, I'll tell you everything about the position function. I mean, sorry, everything about the original function. That's what I'm saying here. This is a big deal, because again, I don't need a lot. Okay, you don't need to give me a lot. Just give me two. Please just tell me the velocity at one point, just one point. Just tell me how fast it was going, and then tell me where it was at one point. If you do that, I'll tell you where it was at every point in time. So I'm going to show you this in action. Okay, I'm going to show you this in action. Let's think about acceleration. If you're on Earth, right, and you take an object and drop it, right, and let it go, right, the only force acting on it is gravity. And the acceleration of gravity on Earth is constant. It is, right? You study this in physics, negative 9.8 meters per second, right? That's what you studied, acceleration of gravity. So if that's the acceleration function for any object on Earth, then I should be able to tell you where that object was at every point in time. But you're going to have to give me two pieces of information. So let's try it. This is pretty awesome. Watch. Let's say we start with the acceleration function, a of t. I'm going to call it a of t. T is time here. Here I want time to be measured in seconds. Okay. The acceleration of gravity is negative. What is it? 9.8 meters per second per second.
I
Something
think
like
it's
that.
9.8 or negative 9.8 or negative 9.82 is what I'm remembering.
Yeah, we
two
say
for
it's
some
negative
reason.
because it's down and not up, okay? So watch, I'm gonna do this for you because I wanna go to, let's look up acceleration of gravity on Earth. Oh. On Earth, there we go. 9.807 meters per second squared, okay? So what I'm gonna do, I'm gonna take this number, I'm gonna convert it to feet per second. And when you do it in feet per second, okay, when you do it in feet per second, it's about 32.17. All right, about 32.17 feet per second squared. So I'm going to do this in feet per second, and I'm going to round it to 32 feet per second squared. Okay, so I'm just taking the acceleration of gravity on Earth, which is usually measured in meters per second squared, and I'm converting it to feet per second squared. Okay, just a conversion. Now, tell me about the velocity function. What can you say about the velocity function? The velocity at any point in time should be equal to what? Well, what's the antiderivative of this?
Negative 32
X.
plus t.
Negative 32
X.
t. We're going to use t. We're going to use t because our variable here is t, time, right? Keep going.
Plus t.
Plus c, right? Plus c. Now, I don't know. I know no information right now about any velocity at any point in time, right? We haven't been given that, right? We haven't been given that, but watch this. This is pretty badass. All right, watch. You tell me, what is v of 0 equal to? What would happen if you plug 0 into that?
Just get C.
You get c, right? You just get negative 32 times 0 plus c, right? Which equals c. But isn't v of 0, like technically, isn't v of 0 the velocity at time equals 0? That's what v of 0 means, which we could also look at as what we call the initial velocity. Because it's the velocity when we start. So if I take an object and I drop it, right? If I just let it go, I'm not giving it any velocity. I'm just dropping it. But I could also throw it downward. And if I throw it downward, then I'm giving it an initial speed right as it comes out of my hand. I'm giving it speed. Or I could throw it upward and give it an initial speed going up. So that initial speed, v of 0, is what c is. So watch what I'm going to write. V of t equals negative 32t plus this constant that I don't know, but here's what I can say. I can say that is the velocity of the object at 0 time. Now, this is a notation that we use in physics, right? This is, you say this v naught, and v naught stands for the velocity at 0 time. And because that's what c is, right? I don't know what v naught is, but that's whatever it is, that's it. That's what c is. Now, let's try and get the position function from this. If we go from here and do the antiderivative, And for position function, I've seen it called different things. I'm going to call it D for, it's like distance. D of t would be the antiderivative of this. What would be the antiderivative of this? Be real careful. Antiderivative of negative 32t would be what?
Wouldn't it be negative 16 squared? 16t squared? Yeah, sorry.
Mhm.
Plus, and then,
Negative 16t squared
and then this.
plus, now this is a constant, Cody. What's the antiderivative of a constant?
Just x,
Okay, what would be the antiderivative of 4?
4x. So I guess this be v naught x or v
V
naught
naught
t.
T, exactly. Because this is a constant, right? It's V naught T. Whatever this number is, it's that times T. Plus what?
C.
C, but I'm going to use capital D because we already used C.
Right. I keep forgetting that.
Okay. So the antiderivative of negative 32t is negative 16t squared. The antiderivative of a constant V naught is V naught times T plus some other constant that I don't know. Now, again, I'm going to ask you, what is D of 0? So plug D of 0 into this, and what do you get?
You're gonna get D again, so this
You're
would
going to
just
get
be,
D,
yeah,
right?
so,
Plug 0 into that, and you get D,
so D
which
naught.
means that D equals D naught. That's the initial what?
The initial position.
Position. Which brings us to this final version of the formula. Which is something hopefully you saw in college algebra. This formula tells you how high off the ground an object is if it's dropped on Earth after a certain amount of time has passed. Does that look familiar to any of y'all? Have y'all seen that before?
Yeah, in physics.
In physics, yeah, in physics, you see that formula. This is your position function. Do you see where it
'Cause
comes from? What is the one thing we needed to know? What's the one thing we
Velocity.
needed to create this?
Or
The
we needed the
acceleration.
acceleration.
Initial.
Acceleration of gravity. That's all we needed to know, right? Everything was dictated by this negative 32, right? And this V naught will always be this constant, and the D naught will always be this constant. What that means is this. If you're on any planet, whether it be the Earth or the moon's not a planet, but if you're on any massive object that has gravitational acceleration, and that gravitational acceleration is constant, right? It's constant, then the position function will always be a what? What type of function?
Wait, if they're both constants, then wouldn't it always be
Parabola.
a position right away?
What do you say, Christian?
It'd be a parabola.
It would be a quadratic.
Or yeah.
Exactly. Yeah, parabola. Yes. Every massive object in the universe that has a constant gravitational acceleration will have a position function. If you drop something on that planet, its position will always be a quadratic function. Why? Because when you start with constant acceleration, your first antiderivative will make a t appear, right? And then your second antiderivative will turn the t into a t squared. So you'll always go from what? Constant to linear to quadratic. Always. So if you want to do the same thing on the moon and get the position function on the moon, you just need to know the acceleration of gravity on the moon. Then you go to the moon, you drop something, and you can figure out, where it'll be at every point in time. It's pretty amazing, if you ask me. All right, let's do another problem. That was just an FYI, okay? I just wanted y'all to see that formula from physics and where it comes from. Okay, so here's another problem. I'm going to tell you that f double prime of x equals, let's go with, I'll make this a little bit challenging. 4x squared minus 8x plus 3. I'm also going to tell you that f of 0, no, I'm going to make it hard. F of 1 equals 8, and f of 2 equals -10. Find f of x.
Was one of those supposed to be a prime?
One of these?
Yeah,
No.
okay, I'm just making sure.
Yeah, this is, I'm glad you noticed that though. Because that's what's making this problem different than the previous one.
Okay,
All right, so we are starting with the second derivative. There it is. I want us to get back to the original function. And all I've given you is information, 2 things I've given you, but this is information about the original function. I have not given you any information about the derivative, have I? So what do? Well, let's just start by taking the antiderivative. Okay, so if we take the antiderivative of this, why don't you take a few seconds to do that? And then I'll call, I want people to volunteer, but I want everyone to have a chance to speak. So if you have it, and if you have the antiderivative and you have not participated yet, go ahead and let me know right now.
It's 4/3 x cubed minus 4x squared plus 3x plus c.
I think that's what you said. You sounded a little bit kind of like you were in a cavern, but is that what you said? 4/3 x cubed minus 4x squared plus 3x
Yeah,
plus.
that's what I said, yeah.
Okay. Okay, I agree. Anybody need help on that? We don't know what C is, right? We don't know what C is, and we don't have a way of getting C because we don't know anything about the derivative, right? Okay, well, let's not panic. Let's try and do the antiderivative now. So if we do the antiderivative, we're going to go back to the original function. And now I'd like for you to take another minute or two, and I'll take a different volunteer to tell me the antiderivative of this. This will be a little tricky. I think those that are out are Cruz, Cody, Jair, Justin, Christian. I think those are the
I'm
only
here.
ones I can think of. No. The ones that are not have already responded.
Oh, okay,
I'm
I'm
looking
thinking
for
I was,
someone other than those to respond to this. Anybody have it yet?
Is
Go
it
ahead.
1/3 x to the 4th minus 4/3 x to the cubed plus 3/2 x to the 2 plus c?
Okay, I agree with you. Everything you've done up to that point is good. Now, Alejandro, C is a constant, right? So like, say it's the number 5. What would the antiderivative of 5 be?
5x
5x. So what would the antiderivative of C be?
cx.
Cx, okay, good. But then we still have the constant for the family, right?
Hmm.
So I need to add to this, not C, but D. You see that?
Okay.
Does everybody see that? So it looks like we're in trouble here because we've got the original function f of x, but there's two things we don't know, C and D. But we have two pieces of information about the original function. So let's use that, okay? So I'm going to say here, but f of 1 equals 8. And what that means is that when I plug 1 into this for x, it needs to spit out 8. So what happens if you plug 1 in for this? Let's see, we get 1/3 minus 4/3 plus 3/2 plus C plus D must equal 8. Right? Just replace all your x's with 1s, right? Because I'm plugging 1 into the original function. And when I do that, it needs to spit out 8. All right, well, this is an equation, isn't it? And it has two unknowns in it. You cannot solve an equation that has two unknowns. Unless what? Can you ever solve an equation that has two unknowns in it? What would you need to solve an equation with two unknowns?
A constant.
I'm gonna guess 2 different values to work with.
Have you ever solved an equation with two unknowns in your life before in algebra?
Would it be a systems of equations?
You would need two equations. You would need two equations with two unknowns in order to solve for the unknowns. Right now we have a single equation, right? This is a single equation with two unknowns, but we only use the first piece of information. If we use the second piece of information, we're going to get a second equation with the same two unknowns in it. And then we're going to have two equations with two unknowns, and we can use college algebra systems of equations to solve. All right, so now I'm going to clean that equation up in a minute, but I'm going to say, but also we have that f of 2 is -10, which means when I plug 2 into this function, it needs to spit out -10. Now that's going to suck. Okay, 2 to the 4th power is 16, so 16 over 3 minus, let's see, 2 cubed is 8 times 4 is 32 over 3, so 32/3. 2 squared is 4, and then I'm going to divide by 2, so that's 2, so that's just 6. Plus, now 2 times c is 2c, plus the d, that needs to be -10. Anybody have any questions on what I just did? Two equations, two unknowns. I'm going to simplify these equations or clean them up. Give myself a little room here. So for this first equation, I could start combining these fractions together, couldn't I? I can start putting them together. I'm not going to. I have an equation. So what I'm going to do is I'm going to clear the fractions. So I'm going to multiply the left side of this equation by 6 and the right side by 6, because I'm looking at the denominators 3 and 2. The least common multiple of both of those is 6. So if I multiply by 6, I should get something that has no fractions anymore. So I distribute here, 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 and then the right side. You understand what I'm doing? Just deciding to not work with fractions. 2 minus, let's see, 6 over there, that should give you 8, plus 9, plus 6c, plus 6d equals 48. -6 plus 3 is 3, so I take 3 away on both sides, I get 6c plus 6d equals 45. Someone can check my math on that. One-third of 6 is 2, 2, 3, 8, 9, yeah. That's -6 plus 9 is 3. Take away 3 on both sides. Yeah, okay. Any questions there? I'm gonna do the same thing on the second equation. Oh, go ahead, Cody.
I was just gonna ask if it would, once we like combine everything, we have like 3 plus 6c plus 60 is equal to 48. Would it be a bad idea to factor out the 3 right away? Just like
Like from here?
well, from the step before I combined everything. But I mean, you could do it from there too, I guess, 2c
Yeah,
plus.
it doesn't
2d.
matter. I mean, I wanted to get a nice equation with nice integer numbers. That's all I wanted to do. I just didn't want to look at fractions.
Fair enough.
So on this one, I'm going to multiply both sides by what? What number? We'll clear the
3.
fractions here.
3.
3. Okay, 3 on both sides. So I distribute here, 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 here. So we get 16 minus 32 plus 18 plus 6c plus 3d equals -30. Let's see, that's -16 plus 18, that's 2. Take 2 away on both sides. All right. We good? Any questions? Anyone disagree? I have 6c plus 6d equals 45. And I have 6c plus 3d equals -32. -16 plus 18 was 2. I took 2 away on both sides. All right, I think I'm good. So now, when you solve a system of equations, when you have two equations and 2 unknowns, you have 2 different methods you can use. You can use elimination or substitution. It's totally up to you. I'm going to do elimination. And the reason I'm doing elimination is because I see the 6 C's are almost identical. So if I decide to multiply the entire first equation by -1, it'll make it a -6c. And then when I add them together, the 6 C's will cancel. So I multiply the top equation by -1. And that's the entire equation gets hit with -1. Then I rewrite the second equation, don't change it at all. And then what I do is I add these 2 equations straight down. This is called elimination. -77. So D is +77 over 3. I know what D is. What do you do once you know D?
You plug it into the original equation.
Yeah,
Or one
go
of
back
them.
to, it doesn't even matter which one you go to. You can go to any of them. I'm going to go to this one right here. I'm going to go here and I'm going to replace D with 77/3. And now I need to solve for C. So again, I don't like the fraction there, so I'm going to multiply both sides by 3. Just because I really don't feel like working with fractions. 18c plus, when I multiply, oh wait, hold on, shit, hold on, time out. I'm out. I
You
didn't
just
even
reduce
notice.
that.
Yeah, that just reduces, that just becomes a 2. Okay, I'm happy. 6c plus, what's 77 times 2?
154?
54?
I think
154?
so. Yeah.
Equals 45. 6c equals, let's see, -109. Is that right? I don't trust my own arithmetic here.
Yeah, it would be -109.
Yeah, negative 109, and then divide by 6. And that's what C is. All right. So I can go now back to, remember where we were? It was this one right here. This is where we were. See if I can squeeze this in here. This is what we knew about the original function. We knew it, but we didn't know what these two values were, right? So now what I can do is I can replace these. D was 77/3. And the number in front of X was negative 109/6. So negative 109/6. There you go. So what I can tell you is this. If you take the derivative of this twice, okay? So take the first derivative and then take the second derivative. When you look at the second derivative, you're going to get back the original thing we started with, okay? That should happen. But more than that, if you plug 1 into this function, you're going to get 8. And if you plug in 2 into this function, you're going to get negative 10. All right. That's kind of interesting, right? That's different than that problem I gave you before, where I gave you some information about the derivative and then the original function. Then it was kind of easy to go backwards. But when I don't give you any information about the derivative and I just give you information about the original function, 2 pieces of information, you have to do a little more work. So here's another way you can say this. I can remember this when I was learning this. I remember this distinctly. I don't know why. I was driving on I-10 with my dad. He was driving. And I told him, I said, you know, it's amazing to me, at least I felt it was amazing, that if all you know is the acceleration of an object, okay, all you know is what's going on with its acceleration, that from that, you can tell me exactly where that object is at every point in time. And all I need to know is where it was at 2 different places in time. That's exactly what this problem is really saying. It's like we have the acceleration, and then you're telling me where it was after 1 second and where it was after 2 seconds. It's position in 2 different positions, right? 2 different points in time where it was. From that, I can tell you everything about where it was at every point in time. To me, that just seems like, wow, you don't need a lot of information to be able to recover exactly where it is at every point in time. Just to me, that blew my mind. My dad was like, yeah, that makes sense. I'm like, bullshit, you don't know what you're talking about, man. I don't know if he understood what I was saying, but I remember the conversation. Okay. All right, I think we're ready to move on. You can now handle, I think, the rest of the problems there. All right. Well, maybe, you know what? Before we move on, I want to show you one more thing. This is just an antiderivative problem. Here's little f of x. I want you to find capital F of x. So this goes back to what we were doing last class at the beginning, or at the beginning of this concept. I give you some function, little f of x, and I want you to find its antiderivative. Right now, all we know, okay, right now, all we know in this class is the power rule, right? If we have x to powers, we can do it. The only other thing we can do is if we recognize this from what we know about derivatives.
Question.
Cody, yes?
Yeah, I was gonna shoot. So couldn't you just turn that into 1 minus x squared to the negative 1/2?
You could. You could turn that into 1 minus x squared to the negative 1/2. Yes, you could. That is the original function. But you can't do anything with that because you can't apply like the -1/2 to both of these because it's a minus between.
Right, the expression.
Yeah, so algebraically, these are equivalent, but it's not going to help you get the antiderivative.
Mhm.
Because what we need is x's to powers, right? That's what we need, x to powers. And we can have pluses and minuses between them, right? Doesn't matter. X to any power. As long as we can split them up and separate them into various powers, we can do each one individually. But here we can't do that. Do you see that? We can't do that here. So the only thing you have then is, do you recognize this as being the derivative of something? Bree, you're shaking your head in agreement. Yes. No, maybe you weren't. You weren't agreeing. So I wanted to bring this up because you probably have forgotten it. We did talk about this. I think the the derivatives of the inverse trig functions, 3.5. We talked about this and I said, don't worry about the homework, just know these derivatives exist. Maybe I need to go back and prove it to you that we did talk about this. Three, 5. We're gonna have to go way back. Here we go. Implicit, it was after implicit. After implicit, no, hold on. What was it?
I mean, I see it could be a difference of squares, maybe like 1 minus x, 1 minus, or 1 plus x, but I don't think that's what you're going for.
Related rates, after related rates. After exponential, hold on. I know I talked about it. I think I did. Maybe I didn't. Y'all help me out here. Look at your formula sheets. Did I talk to y'all about the derivatives of the inverse trig functions? I know I did. Where the hell are they?
Oh, okay, yeah, the,
Right here, yeah, right here, look. Okay, so wait a minute, maybe I didn't.
it's all the way at the bottom. We didn't look at the we didn't look at any of the, inverse hyperbolic stuff.
No, we didn't do this, we didn't do this, but I thought we did these. Inverse trig. I have them marked out, so now I'm confusing myself. I might have to look this up. Okay, so look, let's just take a look at this real quick. What is the derivative of the inverse sine, the arc sine function? 1 over the square root of 1 minus x squared. Do you see that? That is the derivative of the inverse sine. I know I did this. Come on, it's bothering me.
And it happens, sir. I mean, either we're just terrible students and we don't remember, or maybe we
That's what it is.
skipped over it. I mean, whatever you got to
I
tell
remember
yourself.
you like touched on it for like a quick second and you said you're gonna come back to it.
Yeah,
But I don't
I'm
remember
gonna
going
look
over it.
for it on our break. When we take our break, I'm gonna look to see if I actually covered it. Because I feel like I did. It'll make me feel so much better if I can show it to you.
You just told us to look over it on our own, if I remember correctly.
Ah, there we go. I knew I did it. Okay. I still have, it's still in there. All right, so look, I showed you on the 1st of July that we know the derivatives of the 6 regular trig functions, but we have all the inverse trig functions from pre-cal, so we would want to know what the derivatives of those were. And I proved to you, I actually went through the proof of how we can figure out the derivative of inverse sine of x. And I did it using implicit differentiation and this thing called a reference triangle that I told you you're going to use in Cal 2. And then there it is. There it is, right? So that's a derivative of the inverse sine function. Let's see, did I do any more? I said, please remember the derivative of the inverse tangent function because that will come up. And then I pointed you to the notes and I said, just know, here's where they are. There's derivative of inverse sine, there's derivative of inverse tangent. You should probably know the derivative of inverse cosine. Those 3 are the most common used ones right there. So in going back to what I asked you just a minute ago, if I give you this and I ask you to find the general antiderivative, it would be inverse sine of x
Plus C.
plus c.
Let's see.
You could also write arc sine of x plus c. These mean the same thing. Arc sine and inverse sine. All right, now I think I'm ready to move on. Whoa, it's 1:50 already? What the hell? Wait a minute, we started at 1?
1
Okay,
o'clock,
I was
yeah.
like, wait a minute, okay. For some reason, all day today, I thought we started at noon. I don't know why. Okay, so now look, this whole idea of getting antiderivatives, right? Every single time I've given you a function, I ask you to find the antiderivative. I've had to like verbally say, find the antiderivative, or I've had to like write down, find the antiderivative. We need a notation for it, okay? So like if I give you a function f of x, and I ask you to take the derivative, it's very easy, right? I just say, hey, find f prime, and everyone here knows what to do, right? This is the notation for taking a derivative, the little prime mark. So what is the notation to let you know to take the antiderivative, right?
Would be like
It'd
an
be nice if
apostrophe
we
on
had,
the
like,
bottom.
some shorthand notation. What's that?
I was just guessing maybe the apostrophe on the bottom instead of the top.
We could have done a lot of things. I mean, the notation there could have been, an infinite number of things we could have chosen. All right, I'm going to show it to you now. Now, when I show it to you initially, you're going to be like, what? And then later on, it may not happen in this class, but in Cal 2, you'll hopefully your professor will explain why we use the notation. All right, so here it is. If I want you to find the antiderivative of something, here's what I'm going to do. I'm going to write the function down. And then in front of the function, I'm going to put a symbol. And the symbol is going to look like this.
There you go.
It's an S, okay? Think of it as an S that's been stretched out.
I
Okay,
thought that was the integral notation.
that's called the integral sign. Okay, but what I want you to think of it as is me telling you to find the antiderivative, all right? And then there's one more piece of notation I have to put in here to be technically correct. I have to take that and multiply it, put a little, you don't need the dot, it's implied multiplication, but I have to put this thing dx next to it. Now, what is this? I'm going to explain in a moment.
That reminded me of a question I had meant to ask you earlier. So I had saw like when I was doing the homework, there was one problem I was stuck that you didn't have a video. So I went and looked up on Symbolab to see if I could figure out how to work it. And they were doing like the integral sign. I think they had like dx plus c for their formula that they were trying to use or something like that. I guess this answered my question though, where it comes from.
Yeah. Okay, so here are some notes. I'll send you all these notes if they're not in the folder. I'll have to double check. So given a function f of x, if we wish to find the general antiderivative, then we write this right here. Okay. That's the integral sign. Okay, so this symbol right here is called the integral sign. All right. F of x, which is the function you're trying to find the antiderivative, is called the integrand. You may recognize that terminology when you were working with radicals. Like let's say you had a radical back in college algebra. We called this thing the radicand. Well, with an integral, with an antiderivative, the thing you're trying to find the antiderivative of, the function, is called the integrand. The little dx that you write to the outside, that little dx, is called the differential. And it's a complicated idea. I just want you to think of it as this for right now. Think of that dx as kind of telling you what the variable is in the problem. So like dx, right, tells you that x is the variable. But what it really comes from is this. I'm going to try and explain it to you. Do you know how when we took the derivative of something, you always have the chain rule? So like when I ask you to take derivative of x squared, everyone in here says 2x, right? But
Times
technically
dx.
speaking, there's a times 1 next to this, right?
Right, it's the
And
dx over
that's,
dx.
that's the dx, right, next to it. So I want you to look at that dx as being kind of like this dx over dx. It's keeping a special place for the chain rule. You'll see. Just for now, just take it for what it is. Now, the answer to this is the capital F of x, which is the antiderivative of the little f. And then the c, we call this the constant of integration. The constant of integration. This whole thing together is called an indefinite integral. There are, later on, there's things called definite integrals. These are indefinite integrals. And again, that will be clarified later. The process of finding antiderivatives of functions is called integration. So Cal 1, most of your time is spent doing differentiation. Cal 2, you spend almost all of your time doing integration, which is the process of finding antiderivatives. We have already seen this thing called the power rule, that if you're trying to find the antiderivative, let me make this a little bigger. If you're trying to find the antiderivative of x to the n, so now this notation just says, hey, go find me the antiderivative of x to the n. We already know how to do that, right? We know how to do that. We also know that there are common antiderivatives we should know, like what's the antiderivative of cosine? What's the antiderivative of sine? What's the antiderivative of secant squared? What's the antiderivative of e to the x? There's a bunch of things we should already know. But that's it. That's all we have, right? That is it. That is it. So how do we handle more complicated things, right? How do we handle more complicated functions where we're trying to find antiderivatives? So let's try. Okay, let's try. So I'm going to give us a new example here. So we are now officially starting to go down the Cal 2 road. All right. I'm going to give you a function and I'm going to see if maybe you can find the antiderivative of it. Maybe you won't be able to. Let's see. You ready? So I'm telling you right here, please find me the antiderivative. I put the little dx out here. All of that notation is just telling you you need to go find the antiderivative of something. Here it is. Ready? I'm going to let you think about it for just a minute. I want you to be thinking about, is this similar to anything you've had? Can you use the power rule? Is this a common thing you should be able to look at and know? Any thoughts here?
I was thinking we have to set this up into a quotient, so like you treat F or the top like F and the bottom like G, and then you basically just reverse. So get your F prime times G, which is the bottom, and then reverse that for G prime, which is a chain rule times the 2x.
What do you
all
mean
over.
reverse it? I'm not sure what you mean reverse it.
Well, that's how I think of antiderivatives, but so maybe they're wrong.
Yeah,
so-
no, antiderivatives is reversing, but I'm just saying, how are you going to reverse this? If you call the top F and the bottom G, then yeah, you can take the derivative of that, but that's not exactly what we're trying to do, right? We're trying to find the anti. So how do you reverse the quotient rule? That seems hard. Doesn't it, everyone? I'm agreeing with you, Cody. Like I agree.
wait a
but it seems
second.
difficult.
Couldn't we just do product rule with these? Because the opposite of division or quotient would be like multiplication. So could we do that to find the? No, that I don't think that worked, because if you took the derivative of
Well,
that, it wouldn't give you a quotient. So
Yeah, the inverse of the quotient is a product, but that's the inverse of the operation. We're trying to do the inverse or the reversal of the derivative, right? So, all right, can we agree at least that this is not something we know how to do at this point?
yeah, I'm submitting to that. I'm
Like
lost.
even if we took x plus 1 times x plus 1 8 times on the bottom and foiled it all out, multiply that all out, we still couldn't do anything with it, because it would be this term over a bunch of terms. You cannot even split that up into terms.
This is the first one we've had an expression in the bottom.
We've had something, yeah, something complicated. So, all right, look, so Cal 2 is when it comes to integration, finding antiderivatives, Cal 2 can be looked at as 5 basic ideas. All right. The first idea is the power rule. Okay. The power rule, which you already have learned. The power rule in common formulas. Like, you should recognize this. Okay. The antiderivative cosine is sine. That's the first kind of idea of integration. The second idea is called U-Substitution. All right. That's what we're about to do. The next idea is called integration by parts. We're not doing that here. Okay, that's Cal 2. The next idea is called trigonometric integrals and trigonometric substitution. And then the last technique is called partial fraction decomposition. Okay, those are the 5 basic kind of like techniques for learning how to integrate things or finding antiderivatives. There's like 5 basic ideas. Every one of them is different. You use them in different, places. It depends on the problem. All I'm going to try and get you comfortable with, or somewhat comfortable with here in the next day or so, is this idea of U-substitution. So let me show you this. I don't want to say steps, okay? Because when it comes to antiderivatives, I cannot stress this enough. Do you know how in Cal 1, I think you can all agree with me, when you're doing derivatives, everything is just a rule, right? Power rule, right? Bring the power down, subtract 1. Product rule, okay? F prime G plus G prime F. I am a robot. I follow the program, I follow the rule. Quotient rule, right? F prime G minus G prime F over G squared, right? I can do that. Chain rule is a little more complicated, but it's like derivative of outer times derivative inner, the layers, right? It's very mechanical. Antiderivatives does not work this way. This is not going to be, this is the rule for undoing this, and you follow this rule. No, it's these 5 basic ideas, and then you're kind of on your own. Like, you just have to figure out how this all works. It's really different than anything you've done before. You can do it. Obviously, people get through Cal 2, but I'm just trying to prepare you for the mental part of this. You are going to fail more than you succeed when you're first learning this. You're going to crumble up pieces of paper and start over many times. All right, that's part of the process. And you have to get to a comfort level where you look at a problem and you just start seeing it. And that comes with practice and experience with it. All right. So just keep that in mind. I'm never going to provide you a rule. It's not going to be like oh, here's the rule, do this. Okay, it's an idea. So here's the first idea, U-substitution. the general strategy, right? It's a general strategy. What we're going to do is we're going to look at the integrand. Okay, so that means we're just going to look at what we're trying to find the antiderivative of. And when you're looking at it, I want you to try and identify two things. See if it's there. It may not be there, but look for two things. Can you find something? I'm not even telling you what it is. It's just something. Okay, let's call it something. Do you see something? And also separated from that something, somewhere else in the expression, do you see its derivative? Okay. Now, the derivative that you see should be in the numerator and not trapped, meaning you're identifying something, and then you're also seeing its derivative is there, and the derivative that you're seeing is not in the denominator, and it's not trapped. And I mean trapped by, it's not under a square root, it's not in a parenthesis, it's by itself. Okay, so you're
So
looking
like-
for something in its derivative. You're making sure that that derivative piece isn't in the denominator or trapped somewhere. And there's another little caveat to this. That derivative that you're looking at might be off by a constant. So it's okay if it's off by a constant. It might be. Don't worry about it if it is. Cody, you have a
Question.
question? Yeah.
Does that mean we're gonna be looking purely for if like the powers match up for it? It's like if I see this and then like its derivatives up there, it's right with the power then?
Yeah, I mean,
Are you
it's just whatever the derivative. I can't say power because it doesn't necessarily have to be a power.
Or wait, when you say the constant, are you talking about like, it would be like for this problem, if it had 2x plus 1 on the top, or would it be like a difference of like 3x? or
Well,
something?
let's do some problems. Let me give me an opportunity to run through a couple of problems and see how this strategy works.
Okay,
I'll refer back to this. This is just the general idea. Once we do examples, I think it'll start to become more clear, hopefully. Okay, so we're looking for something. We're looking to see if the derivative of that something is sitting there somewhere. It's not trapped. It's not in the denominator. And you know what? That something, the derivative of it, it could be off by a constant. That's not a big deal. And then once we've identified that, what we're going to do is make a U-substitution. And we're going to let U be the something that we found in the very beginning. The something that we found, not its derivative, the something. We're going to replace that with U, and then we're going to go for it. All right. And you don't know what I mean by that. You ready? Let's do the problem. This is fun. Okay, so I'm looking at this. I'm first ruling out all the other stuff. No power rule, no something I should know from Cal 1. I realize we're still in Cal 1, but so I'm looking at that and I'm like, oh, wait a minute, hold on. I see something, right? X squared, I see that. And I see its derivative is 2x right there. I see that, right? The something here is the x squared and the 2x is its derivative. Now 2x is in the numerator, right? So it's not in the denominator, that's good. And it's not trapped. So that 2x is not like if this was square root of 2x, that would be bad, but it's not, okay? So it's nice and clean. Do y'all see that? So I could right now let U be x squared, all right? I'm not going to though, because watch. What if I look at the entire expression in the parenthesis as my something, x squared plus 1? Isn't the derivative still 2x? So I could have said that something was x squared or the x squared plus 1. What you're going to try and do is grab as much as you can without grabbing too much. For example, if I try and take the x squared plus 1 to the 8th as my something, that's too much. Because what's the derivative of x squared plus 1 to the 8th?
8 times x squared
8
plus 1 times
X
2x.
squared plus 1 to the 7th. Chain
Or,
rule,
yeah,
right?
sorry, yep, 7th.
Right? So it's too much. So it's this delicate balancing act where you're going to try and identify the something, get as much as you can without too much, without going too far. All right. Y'all good with this? I'm going to make my substitution. Over here, I'm going to let U be equal to x squared plus 1. So I'm not writing the word let, but that's what I'm doing. Now, making a substitution is something we've done in math a lot of times. In college algebra, sometimes we make substitutions to make problems easier. We're doing the same thing here. So now I look at this. This is a new equation, right? And what we're going to do is implicit differentiation. So I'm going to take the derivative on the left and right with respect to x. So du dx is the derivative of the left. And what is the derivative of the right with respect to x?
2x.
2x. That's it, right? So there is the something, and there is the derivative of it, right? Happens to be match up pretty good, yes? Now I'm going to do one more thing. I'm going to take this equation, the second equation I got, and I'm going to multiply both sides by that dx. See that? du over dx, I multiply left and right by dx, and I get this. Now, I'm going to go back to the original integral, and I want to rewrite it so you can see this. Because the 2x was not trapped, right? It was in the numerator. It was up in the numerator, not trapped. Because of that, I could always slide it off to the side like this, couldn't I?
Yep.
And do you all now see what we have here? We have the x squared plus 1, right? Is that. And we have the 2x dx is this. Right? Right?
Mm-hmm.
So I'm going to now make the substitution. I am going to rewrite this, but instead of having x's in my integral, I'm going to have u's. So this first part gets rewritten as 1 over what? What's the yellow part?
Yeah, 1 over u to the 8th.
U, right? So this is 1 over u to the 8th times 2x dx, which is what?
Du.
du. So now what we have is, hey, find the antiderivative of 1 over u to the 8th where you're treating u like the variable. So this is just kind of, again, we're just going to now determine if we can find the antiderivative of that. Can you?
Mm-hmm.
Isn't that u to the -8?
Yep.
And can't you just use the power rule on that?
Right.
Right? You can use the power rule on that. Now, since we can use the power rule, I'm about to find the antiderivative. So watch what my next line is. It'll be u to what power? What's the power going to be here if I do the power rule?
For antiderivative, it'll be -7.
Antiderivative. It's the antiderivative. So we add 1 to that.
Mm-hmm.
So -7. But in front, what do we have to put?
1 over -7.
1 over -7, the reciprocal. Right? And then plus
C.
C. Very important that you understand that from this step to this step, we did the antiderivative, okay? Students always ask me, what happened to the du? They always say, what happened to the du? Nothing happened to the du. This is the thing we're trying to find the antiderivative of, okay? So the antiderivative of that becomes this. If you want the du to become something, all right, even though this is not technically right, if you just in your mind say du has to go and become something, then make that be your plus c so you don't forget the plus c, all right? Now we're not done because our answer is in terms of u and our original problem was in terms of x, right?
And we just replace the u with the x squared plus 1.
So now we replace that u. I'm going to rewrite this as -1/7. I'm going to put the negative way out front. And then u, which was x squared plus 1 to the -7 plus c. There it is. If you wanted to, you could rewrite this way. It would still be correct, of course. That's just me taking this whole thing, dropping it to the bottom. Make it join with the 7, put the negative up top. Both of those are correct. Now, is that correct? Is that the correct answer? Well, what can we do to check?
Take the derivative of it.
Take the derivative, right? Okay, so let's do a quick derivative of this. If I ask you to take derivative of that right there, chain rule, right? -7 would come out. So we would have -1/7 already out there. We bring the -7 out, and then it would be x squared plus 1 to what power? Taking
-8.
derivative. -8, subtract 1, times chain rule, derivative of what's inside,
2x.
2x. And notice what happens out on the front, right? The -1/7 and the -7, that all goes away and just becomes a 1. So you're left with just this times 2x. And if you drop the x squared plus 1 down, this was the original, well, not there, one more line up. That was that. Okay. So this is why we always tell our Cal 1 students, if you're having trouble taking derivatives and you go into Cal 2, it's going to be hard because you have to see something in its derivative, right? Like if you don't know what the derivative of something looks like, then how are you going to do substitution, right? Let's do another one. God, this is fun. All right. Let's find the antiderivative of, let's do the same problem, but I'm gonna just change it a little bit. Let's do it this way. X over x squared plus 1 to the 8th dx. That's the same exact problem, but I didn't put a 2x up top, right? Is it the same? Wait, was it 7? I forgot already now. Yeah, that was this, right? It was this, but I took the 2 out of there. Okay. So I play the same game and I notice, okay, by looking, I notice that if I take x squared plus 1 to be my u, the derivative of that is 2x, right? Now I don't have 2x, I have 1x, right? I have 1x, but I'm off by a constant and that's okay. Let's see why it's okay. I make my substitution, use x squared plus 1. I take the derivative of that with respect to x and I get 2x. I multiply both sides by dx and I get 2x dx. Nothing there has changed. That's all the same. I have that this yellow part matches, right? X squared plus 1 is this. That will be replaced with u. The problem I have though now is that when I rewrite this, x dx, right? When I do x dx here, bring that x out, that doesn't match this, does it? This doesn't match. Simple fix. Divide both sides by 2. Okay? If you divide both sides by 2, you get 1/2 du equals x dx. And now they match. So how does that change things? When I come here and I rewrite this, I'll go 1 over u to the 8th, but the green part gets replaced with what?
1/2 du.
1/2 du. Okay, 1/2 du. And now this is the first time I've done this, okay? So I want you to just see what I do and tell me what you think. I took this 1/2 and I just brought it completely outside of this integral sign. And I said, hey, that 1/2 is a constant that's attached to this function. And I know that when it comes to antiderivatives and derivatives, both ways, the constants come for the ride, don't they?
Yeah, I was gonna say you just pulled it out because it was a constant.
That's right. So I'm just going to now bring that 1/2 out, and then I'm going to do this. I already did that problem, right? We just did that, right? Right here, right? We just did this, and it came out to be this answer, right? So we're going to have the same answer, but what are we going to have in front of it?
Times 1/2.
Times 1/2. So we're going to have, you know, this is obviously ... See the previous page. This is going to be 1/2. times -1/7 x squared plus 1 to the -7 plus c. And then you could put these together and get -1/14. So do y'all see now why being off by a constant really doesn't matter? That you can always scale right here. Right here, I scaled both sides. I scaled in order to make it look the way I wanted it to look. Let me do one more. What if we do the same exact problem, but now I put 3x out front, 3x on top? Well, same issue, right? If we do the u is x squared plus 1, and du over dx is 2x, which means that u is equal to 2x dx. I don't have 2x dx, right? I don't have 2x dx. I have 3x dx. So here's what I would do on my next line. I'd rewrite this integral. I pull the 3 out. I pull the 3 out because I don't need that. The 3 is a constant. You can come from the right. So I'm just going to pull the 3 out. And then I do this. Oh, sorry, I forgot the x there. So I take that x, I slide it here. And then I pull the 3 out front. And then now this problem right here is the previous problem we just did. Right? We just did that problem. Okay. What do y'all think so far? I mean, we're just at the very beginning of this, but so far seem reasonable. Anything crazy?
It's kind of a, like I don't want to use the term culture shock, but it's just a little different from that. There's no real set rules like the derivatives. I mean, for lack of a better term, I know the math and the mathematics guy in you is going to kill me for this, but the derivatives feel much more linear, much more straightforward. I have this, so I do this. Whereas these are more of, I have no idea what the hell I've got. I got to make things. I've got to make pieces.
Yep, exactly. That's exactly right. And that's what I was saying. Cal 1, the stuff you learn is very mechanical. It's very procedural. And Cal 2 is requires more creativity. And it takes more persistence because you're going to screw it up. You know, like you're going to make mistakes and start over. More than you did in Cal 1.
Yeah.
Okay,
Cal
how
1,
about this? Go ahead. What?
I was just gonna say Cal 1 is definitely giving me the building blocks vibe now, like for sure. For 2.
Okay, look at this one right here. Take a minute to look at it. It looks unassuming. Is that the right word? Unassuming? Yeah, I think that's one. But there's a little technicality in here we have to be careful with.
Chain rule.
Yeah, so see if you can't get it. I'm gonna give you a minute just to think. Okay, I think that's enough time to think. So maybe you look at that and you say, okay, wait, I know what the antiderivative of cosine is. The antiderivative of cosine is sine. So you might think to yourself, oh, the answer here is just going to be sine of 5x plus c. What's wrong with that though?
Wasn't it supposed to be negative sign?
Mm-mm.
I know I'm
You
thinking
got
that.
the 5x, the derivative of the inside.
Yeah, so if you took the derivative of this, I agree, you would get cosine of 5x, but then you have to take derivative of the 5x, which would give you a 5. You don't have a 5 in the integrand, right? There's no 5 out here. If there were a 5 here, I would agree, then yes, this is the right answer, but there is no 5 here. So you would have to kill that 5 off, right? By putting a 1/5 in front of this. Right? So this is not as simple as it looks. So here's what I'm going to do. I want you to look at this as a substitution problem. It is a substitution problem. Do you see something and its derivative? It's tricky, but it's there. So what's the something?
Something's gonna be the cosine of 5x.
Okay,
5x.
then you need to see its derivative. What's the derivative of cosine of 5x?
Well, that'd be sine of 5x, which we don't
Yeah, and
see.
you don't have a sine, right? So you grab too much there. Can't grab the whole cosine. So what else is there?
5x?
Looks like you want to say something. No? Jair, 5x?
Yeah.
Okay, so Jair, if you're going to say u is 5x, what's the derivative of 5x?
5?
5. Okay, do you see a 5 here?
No.
No,
we just-
but you see a 1, don't you?
I was gonna say, grab the x.
You're off by 5. So like there's a 1 right there, right? So Jair says, I'm gonna let u be 5x. The derivative of that's 5. I have a 1, so I'm off by 5. It's okay to be off by 5. You just can't be off by anything more than a constant. Jair, does that make sense?
Sort of.
Let me write it down. U is equal to 5x. That's what Jair said. Okay, the derivative of that, Jair, with respect to x, you said was 5, right? I'm going to multiply both sides by dx and get 5 dx. But Jair, when you look at this problem, it's cosine of 5x times, you don't have 5 dx, you have 1 dx, right? You would like it to just be 5 dx, it's a 1 dx, so can you make this a 1 dx over here? What do you do to get rid of the 5?
You divide it.
Divide both sides by 5. So you go 1/5 here, divide by 5, and now you have 1/5 du equals dx. Which means you can replace 5x with u, and you can replace 1 dx, well, that's 1 dx, with 1/5 du.
Okay.
Does that all make sense to everyone?
Yeah, but I don't know. I was thinking we'd grab the x just because I knew there was a 1 somewhere, but I forgot about the whole constant thing.
So this becomes cosine of u times 1/5 du. Rewriting the integral, replacing the 5x with u, replacing the 1 dx with 1/5 du. The 1/5 is a constant. I'm going to bring it out. And now that is something we should be able to do. The antiderivative of cosine of u is just sine of u plus a constant. But don't forget, we have the 1/5 out front. So 1/5 sine of u plus our constant of integration. And now replace u with 5x.
So just a question, I guess. So like I see it's like you're basically out in front in this case at least, it's the reciprocal of what we had in the for our u basically, or the value within the parentheses. Would that ever be a time where that's not going to match up? So like, say I had cosine of 3x, would it still be like 1/3 sine of 3x plus c? Is that like a rule, or not like a rule, a pattern I'm seeing, or is it just coincidence for this?
You are seeing a pattern, and I was just about to challenge y'all to think about this. Okay. Let me give you another problem. Okay. Very similar. What if I said cosine of 10x dx? Well, we could do the same thing, couldn't we? U is 10x. The derivative of that is 10. We're off by 10. So we would have to divide by 10. And so we know we would have to scale this by 1/10, right?
Mhm.
So this should turn out to be 1/10 sine of 10x plus c, just from what we did in the previous problem, right? So I think what Cody's asking is he seeing a pattern here, right? Will this work for any cosine of any number times x? And the answer is yes, it will. Let's do another one. What about cosine of negative 3x dx? Well, the antiderivative of that, this negative 3 is going to be a problem, right? So what are we going to have out in front of it? We had 10 here, we needed a 1/10. Negative 3, we need what? Negative 1/3. You can put the 3 on the top or the bottom. Sine of negative 3x plus c. So now Cody's question. What about cosine of any constant a times x dx? It should be what?
1 over
One.
a
Yeah.
1 over a
sine of
Sine of
x
ax
plus c.
plus c. And now I would box this and tell you that's like a formula you should know, but I'm going to go one step further. Watch. That would work for not only ax, but ax plus b. That would work. What I'm saying is if this was linear in here, if that's a linear expression, then imagine that that was a linear expression, right? When you take the derivative of this, what would you take? What would, if you let the u be this, right? Do the substitution. If u is this, then what's the derivative of this going to be?
AU?
Just a, right?
Yeah, A, sorry, yeah.
Just a, right? Because the b doesn't matter. When you take its derivative, it goes away. So you'll still have to scale by the a, but you don't have to worry about the plus b. So this would become 1 over a sine of ax plus b plus c. I hear thunder. Now that I would try and get into your brain as soon as possible. Let me show you one more example of that, just so you make sure you get it. If I ask you for the antiderivative cosine of pi x plus 4. If you recognize that the pi x plus 4 is a linear expression, do you all agree that this is just a number in front of x plus a number that's linear?
Yeah.
We should know then that the antiderivative of this is going to be 1 over the a, which in this case is pi, and then sine of everything that was in there. And if you don't believe it, okay, if you don't believe it, just take the derivative of this. Okay, take derivative and you'll see it comes out to be this. This is a subtle thing, but do you see why it's so important to understand Cal 1? If you take the derivative of this, right, the constant stays here. I'm just going to think through this. The derivative of this is cosine of it. And then times chain rule, derivative of the inside, because it's linear, you're going to get a pi here. And that pi go away, which is why you need the 1 over pi out front. Do you think this works for any function that you know the antiderivative of? Like, for example, if I give you, let's say, e to the pi x plus 4 dx, do you know the antiderivative of e?
Yeah,
E to
it's,
something should be itself, right?
and then in it times the derivative of that something.
I'm saying, what's the antiderivative, right? What's the antiderivative of e should be itself, right? The
Oh, yeah, yeah, it's
antiderivative of e to the x should be itself. Why? Because the derivative of e to the x is e to the x. But what I'm saying is, if we do e to a linear, right? That's linear up there again. Then what are we going to have to scale by? What are we going to need out front?
The 1 over pi.
The 1 over pi again. And then just the antiderivative of this, which is e to the pi x plus 4. plus C. Okay, I'm getting a little bit too far away from where I want to go. Let's take our break, then we'll come back and we're going to do more substitutions. All right. 10 minutes.
Hey, Brian, you there?
What's up?
You keep up with spoilers at all?
On what?
Anything, I guess One Piece for this specific instance.
Spoilers, and like theories, you mean? Like, what do you mean by spoilers?
No, like actual, like I got the spoilers off Reddit for this week's chapter. Some hints of what's
Oh,
being
nah.
dropped.
Well, wait, there's no chapter this week, so it can't be.
Well, I guess next week, whenever the next chapter is.
Oh, yeah.
But because it does get released earlier in Japan too, but not quite this early, I don't think. I don't think it's Golden Week, is it? No, Golden Week's in like May, I think.
Mm.
Probably just a holiday or something. But yeah, apparently we're gonna.
No,
we
it
don't
was
know-
we're
Go
not
ahead.
getting one for this week because of the Olympics, isn't that right?
Oh, that might be it, actually. I completely forgot about
they-
the Olympics.
Yeah, it's the Olympics. They're not doing a shonen jump this week.
Yeah, I don't think name or anything was confirmed, but I guess Oda's not gonna wait too long. We're gonna apparently learn what Yamato's fruit is, apparently. I mean, I didn't really think we would have to wait that long, but
I mean,
I don't know. You can never tell with Oda. I mean, there was like 500 chapters between when Doflamingo's ability was first displayed,
yeah.
and then I mean,
Back at what is it? That old island? God, what is it?
yeah, with the Jaya arc, I think it was. Jaya,
Yeah,
but
it was right before then. God,
Well-
what is that island called?
I'm
weird.
trying to remember. Not Whiskey Peak. That's from That's from.
That's Alabasta.
Yeah.
yeah.
I know what you're talking about. It's where he was messing with Bellamy. But what I don't
Yeah,
remember
and
the
then
name, but-
descendant of what's his face?
I mean, Skypea.
No,
we're
this
talking about
was
Skype.
this was right at the beginning of the arc where they're
Yeah.
at that town. I gotta look it up.
Yeah,
Yeah,
I can't
yeah.
remember.
It's pissing me off.
Can't remember the name. Hold on, let me grab a drink real quick.
Mocktown, that's what it was. Mocktown. Freaking. You watch any other anime, Alejandro, or read any other manga?
Yeah, I'm reading the Dragon Ball Super manga on Viz, the Boruto manga, and My Hero.
Yeah, My Hero. I don't know if you're caught up with it or not, but I don't know. For me, it's getting kind of weird. But and then Super, it kind of messes with me how like they had a whole 100+ episodes series, and then like the manga is kind of doing its own thing, completely different. But
Wait,
it
what's
is what
up?
it is. We're talking about Super, and I was just saying how it's weird for me
Mhm.
that the manga's got a completely alternative storyline compared to the show itself.
Yeah, I'm wondering if they're going to continue the anime based on the manga because they got like 2 more arcs going on with manga.
Yeah. I don't know, because I haven't looked too much into the DBS manga, but I don't know. Does it even have the Tournament of Power at all in it, or what?
I can't stand Dragon Ball. I actually can't. Like, I don't feel like there's a story to it at all. I'm just
bro.
kind of like,
Part of it is like when you're young, it's just all hype. And then now for me, I recognize the story is subpar. The plot sucks ass, but there's too much nostalgia for me. I just like go back to sitting there trying to go Super Saiyan with my friends on the playground in like third grade.
yeah, but it's just
things
like,
that.
I mean, like, yeah, I know it like the popularity, but it's like with this stuff, it's just like, man, it's so
Alright.
hard to sit.
I got a
sit through,
question then
man.
for
Like,
you.
Mhm.
This is gonna pretty much, if we stay friends, this will determine the future of the friendship here. Did you like Seven Deadly Sins?
I did.
Me too.
Goodness.
That was pretty good. I'm not gonna say like it's an amazing story. I enjoyed it. It was entertaining.
I liked it in the beginning, but then at the end, everything, it was just, it was retarded to me. Like Arthur's, then now I don't know.
No, yeah, it was bad towards the end. It was still entertaining though for me. I-
Yeah. All right.
Would-
Favorite.
Like, there's just
I might be lagging, but
in my computer, I was switching
oh, okay.
screen things and it screws up sometimes. Yeah, but what is like really with Dragon Ball? Like, what is the ultimate end goal? Like, just to become the strongest
Really,
thing ever? Like,
not
Yeah,
even
I guess.
at this point. at this point, it's just more about, it's not even about reaching a goal. At this point,
Yeah.
the show just really wraps around the idea of constant improvement. And that's about all you're gonna get from it. Like I said, it's nostalgia for me, but there's plenty of series that are much better. I don't know.
The JoJo though. JoJo though.
I've been
Love-
trying to get into JoJo. I like,
So good.
the
So
art's
good.
just a little weird for me, but like, I gotta just get
The
past
dude's
it.
a great artist. The dude, I love his art. His art is
I
so
like,
good.
I like his art in the manga and stuff. It's just like,
His character design.
yeah, I like all the art and his designs and everything. It's, I guess really what it is it's all the color and the CGI in the JoJo that kind of throws me off. I'm not, like, I love
There's
the
not a whole lot
monster.
of CGI.
Well, a little bit, but maybe not. Maybe it's what I'm
Yeah.
wrong, but I don't know, I liked Monster, that 74 episode. It's like,
Oh,
Justin,
yeah.
what
thriller.
were you doing?
Huh?
Justin, what were you doing?
I have a
Is that-
laser pointer.
That a laser? That's
Yeah.
illegal. That's illegal. You can't point that in my eyes like that.
You know,
Or do I have to be flying a helicopter? I don't remember. What is
I think it's illegal to point at any airborne object being piloted by somebody,
it?
but
they'll get blinded.
Yeah, don't let us see you on the news later. Some thermal image. Like,
They'll
yeah, I
have to
recognize that guy.
and then someone will be on the news. Yeah, I went to school with him. He was a great guy. Don't know what happened. He just fell off the wagon or something.
Okay, all right, y'all ready to get more into this? All right, here we go. So I'm just gonna make these up. How about we go with this? The square root of natural log of x over x dx. Right, so you have to rule out that this isn't something that you recognize, like, oh yeah, I can do this, or oh, I can do that, or
Okay, so then I guess you wouldn't want to just like split it up 1 over x times square root of ln x and then well, no, that wouldn't be the derivative. Never mind.
well, I actually kind of do like what you just said. You could split this up as square root of ln of x times 1 over x dx. I do agree you could do that, and I kind of like that, actually.
Yeah, I was going with it. I was thinking, well, like 1 over x, well, ln x, the derivative of that is 1 over x. So that's what I was
Okay,
thinking.
so you just found something in its derivative. Something is ln of x, right? The derivative of ln of x is 1 over x, which you have right there. So we can make a substitution. U is ln of x. The derivative of that is 1 over x dx. Okay, everyone, I just skipped a step. Prior to right now, every time I've done this step, I've written du over dx equals, and then I took the derivative 1 over x. And then my next step was to multiply both sides by dx. I'm going to do that every single time. I'm going to multiply both sides by dx every single time. So from now on, I'm going to stop writing du over dx, and I'm just going to write the derivative and slap the dx onto it to just save myself this step. Does that make sense? Just so I don't have to do it. Things match exactly, right? This green matches exactly with that green. This yellow matches exactly with that yellow. And so now we can rewrite the problem. This becomes the antiderivative of the square root of the yellow thing, which is u, times 1 over x dx, which is exactly du. And that becomes the antiderivative of u to the half du. I wrote it as u to the half because I'm going to use the power rule for antiderivatives. So this becomes u, I need to add 1 to a half, that gives me 3 halves. And out front, I need the reciprocal 2/3, and then I need my plus c. And then the last step would be to replace the u with whatever u was, and u is natural log. So I'm going to put natural log of x raised to the 3/2 plus c.
Just, do we also want to be in the habit of putting natural log of absolute or the absolute value of the natural log of x?
We did not take the antiderivative of 1 over x. We never did that, right?
Right.
So if we take the antiderivative of 1 over x, then we will.
Okay.
Okay, good. All right. So let's do another one. How about the antiderivative of sine x over 1 plus cosine squared x dx. Now that's 1 plus cosine squared x, not 1 minus cosine squared x. If it were 1 minus cosine squared x, then I could turn 1 minus cosine squared x into sine squared x, and then this problem would be a little easier. Well, and actually it might be harder because then that would be cosecant. We don't know the antiderivative of cosecant, but it's not a minus, it's plus. So you can't split this up into 2 fractions because you have a single term on the top, 2 on the bottom. Can't split it up. So Bree, what do you see? Do you see something in its derivative?
1 plus cosine squared x is equal right there.
So is that what you're saying? Maybe your something is?
Yeah.
Okay, let's think that through. If we did that,
Oh, wait.
oh, you're changing your mind?
No. Just.
If that were the case, what's the derivative of that? The derivative of that would be, we have some chain rule there, don't we? Because of the cosine squared x.
Yeah.
We would have like what, 2 cosine
cosine.
x times, what's the derivative of cosine?
Sine.
Negative
Oh,
sine.
negative sine.
Okay, so that's a problem because if this is your something, Bree, the derivative of it is very complicated and all you have is a sine x. Do you see that?
Okay.
You need to be able to see something and its derivative. I think that's too much.
I got it.
Yeah, I was just saying, can you?
Christian,
It's
what do
just
you have?
Cosine x on the bottom,
Wait, say again?
and it's just like 1 cosine x, like not the plus one. It's just cosine x, and then the sine.
Just cosine x.
Yeah, just cosine x, because you
So you
could
want
rewrite
u to be
that
cosine
as.
of x?
Would it still be the same thing?
Well, he's saying just the
It's off
cosine.
by just a constant. Yeah.
So we're looking at, I guess, Bree, what Christian's doing is saying, we're looking at that cosine squared x as being cosine of x squared. That's the same thing, right?
Yeah.
So
Okay.
if you do that, then you said, Christian, the derivative of that would be negative sine
Negative
x
sine x.
dx. Notice again, I'm putting the dx on the other side, everyone. And we're off by a constant. So I think what Christian is seeing is that you can rewrite this as 1 over 1 plus cosine of x squared. Then the sine x can be slid out to the side like this, sine x dx. And Christian is saying that he's almost got it, right? We're just off with the negative sign. So what do you do then? Christian, you're off by this constant. So how are you going to resolve that?
Would be by the reciprocal, which would just be, you just put a -1 up front.
Yeah, just basically multiply both sides by -1. So this becomes negative on this side and positive on this side. Just multiply both sides of that equation by -1 or divide by -1. It's the same effect. So now Christian's got cosine x, that's the u. And then Christian's got the sine x dx matches exactly here, sine x dx. So Christian, tell me what the new integral is going to look like.
It's gonna be 1 over 1 plus u squared
Mm-hmm.
with du out to the side.
Du, and is it du or negative du?
Negative du.
Negative du. So is it all right, Christian, if instead of putting negative du, I put a negative 1 on the outside of the integral?
Yeah, that works.
So instead of putting negative du here, everyone, put the negative out front. Okay, that's good. Now, before we proceed, I want to just point something out. What about letting, instead of doing this substitution, what if I would have let u be the sine x? Because if you look at it this way, if u is sine x, what's the derivative of that? What's the derivative of sine?
Cosine.
Cosine of x, right? Dx. And I see a cosine, right? But what's wrong with that?
It's on the bottom.
Yeah, it's in
It's
the
on the bottom.
denominator.
Remember I said, when you pick the something, right? The something was the sine x. Its derivative, cosine x, better not be in the denominator, better not be trapped. And it is. It's trapped in here. And the thing is, every time we've done these problems, we've always taken the derivative piece, right? And we've always slid it to the outside like this. And if it's trapped on the bottom, you won't be able to slide it to the outside. So even though the derivative of sine is cosine, that's not the correct substitution. Substitution needs to be cosine of x, and the derivative of it is negative sine, and you're off by a negative or whatever, right? Okay, now we're not done, because we need to know what the antiderivative of that is, right? And you can't split it into two fractions, right? You can't do 1 over 1 plus 1 over u squared. You can't do that. Does anybody recognize this?
It's one of the inverse functions.
Yeah.
Yeah,
gonna say it's one of them.
It's the one, this right here, July 1st, I put 4 stars next to it, right? 4 stars, that this would come up in Cal 2. So the derivative of arctangent of x is 1 over 1 plus x squared, which means that the antiderivative of this is arctangent of x. And so with that knowledge, we can say that this is equal to the -1. Okay, we're taking the antiderivative now. And then the antiderivative of that is arctangent of what? Not x, u.
Plus c.
c. And that's equal to negative, I don't really need -1, I'm just gonna put negative tangent inverse of u, but u was cosine of x plus c. There you go. Okay, you ready for another one? Bree, did that make sense? You're on mute.
Sorry. Yeah, I did for everything. I don't know how you got the, I mean, I know that the invert or the derivative of cosine is negative sine x. I guess like, oh, you didn't take the square. Oh, okay. Never mind. I get it now.
Yeah, I just multiply both sides by -1.
No, it wasn't that. I was like, I wrote it down as like I took u equals cosine x and then squared. That's
Squared,
where I
okay,
was
yeah.
like, got
Yeah.
confused. I'm good now.
Okay, good. All right, let's see here. All right, x cubed cosine of x to the 4th plus 1 over the square root of sine of x to the 4th plus 1 dx. Let's see. Brian, I think I'm just going to start in the top left corner of my screen here. Brian, I don't think we've heard from you today. Can you see the problem?
I'm still writing it down real quick.
Yep,
I'm
take your
trying.
time. Looking for something in its derivative.
Well, it's because it's a product rule in the top.
Yeah, don't worry about the multiplication, the product, the quotient. Just try and look for something and then hope to see its derivative somewhere else. And it's okay to be off by a constant. And that derivative just needs to be like not trapped.
I mean the cosine of well, it's a cosine of are you, so you're asking for like the derivative of the, are you asking for like the first step? What do you, I'm not a,
Why don't we do this? Why don't you just watch this one and I'll get you on the next one. Okay.
all right.
Because what I want is I want someone to take a swing. Okay. So, you know, this
I
Cal
got
2
it.
stuff, you got to be willing to take a swing and do something, right? You can't hit a home run unless you take a swing, right? You can't win the lottery if you don't play. So it's that first initial step of trying something, right? So I'm going to move to the next person. I know some of you have it already. I'm going to go with Naja because you're the next one on my screen. Do you see something in its derivative?
I see like the sine to the x4th plus 1 and like
Okay.
the derivative is the top, right?
What is the derivative of that? So can you do that in your head? If
Yeah.
you're saying that you're going to make the substitution u is sine of x to the 4th plus 1, what would the derivative of that be?
Cosine to the x4th plus 1 times x to the 3rd.
Times 4x to the 3rd,
Yes, 4x.
right? Okay, so Naja has actually grabbed a lot. She grabbed this whole thing right here because Naja, I guess, already kind of mentally knows that if we grab that, right? Naja said that the derivative of that would be chain rule, cosine of x to the 4th plus 1 times 4x cubed. And then remember the dx that I'm going to bring over. So Naja sees this, right? I'm speaking for you, Naja, but you saw that this right here, and you see that you almost have it here,
Yes.
right? You almost have it. You have an x cubed. Well, it's in front. That's okay. I mean, because that can move. You just don't have the 4, right? The 4 is not up here. So I guess another way I could look at this, or another way we could look at this, is that Naja was actually seeing that you could rewrite this with that whole thing here, just that whole thing pulled off to the side. And then we almost match, like this right here is this, okay? And then the derivative, we're off by 4, so we'll just, divide both sides by 4. And that should give us an exact match. This whole thing will match. Okay, so let me ask a question. Honest reaction here. Just raise your hand if you have your camera on. How many of you saw that substitution? 3. Okay.
I saw it a different way.
Okay, that's not the only substitution. There's another way. So 3 of you saw the substitution. Now, if I ask you, how did you see that? How did y'all see that? Naja, how did you see that?
I mean, I have experience with integrals, so
Okay, so you have some experience.
yeah.
All right, Christian?
In my head, I just kind of took the derivative of the bottom one and
Mhm.
then saw I was missing the 4, and that was it.
Jair, you did the same thing? Okay. I can't teach that, okay? I cannot teach that. That's the issue with Cal 2. I cannot teach you how to process this information mentally. I can't do that. You either have that foundation with derivatives or you don't. And if you have that weakness, then that's what Cal 2 exposes. So I'm going to continue with this. This substitution is actually the most efficient way to do the problem, but there's another way to do it. I'm going to do it after we do this one. I'm going to show you a different way to do it. All right. Let's finish it up though. All right, so here we go. Rewriting the problem, everything in green here gets replaced. So I'm going to have integral. This will be 1 over the square root of u. That's this part. And then the green part becomes 1/4 du. I'm going to bring the 1/4 out and put the du here. That's 1/4 integral u to the -1/2 du. And now I can apply the power rule. So no more integral sign, 1/4 comes for the ride. I'm going to have u, I need to add 1 to -1/2. So I'm going to add 1, it gives me 1/2. I have to multiply by the reciprocal out front, 2 over 1, and I have to do plus c. And then the 1/4 times 2 gives you 1/2. U, what was u? I forgot. It was the sine thing, wasn't it?
Mhm.
Sine of x to the 4th plus 1. All of that to the 1/2. That's the same as the square root plus c. There it is.
Wait, why did we get? Oh no, you just did it with the. Never mind.
So I'm not trying to discourage you with me saying, you know, I can't teach you to think that way. I'm just being very honest with you. It's one of those things like students, just some students will just see it and some students just really have a hard time seeing it. Let me ask, why did we not pick the cosine of x to the 4th plus 1? Why not pick that as u? The derivative of that would have been negative sine, right? So we would have been
Yeah.
off by a constant. But where's the sign?
It's in the denominator.
It's on the denominator. It's underneath the root. It's trapped. That's not the way to go. Okay, so that's why we didn't take the sine of x, the cosine of x to the 4th plus 1.
Could I take a guess
now-
at the other method?
What's that?
I said I was just wondering if I could take a guess at the other
Yeah,
version
go
you guys
ahead.
do.
So the other method,
I
the
was
other
just
approach.
thinking. I was just thinking you pull the x to the 4th out of the cosine, and then the x to the 3rd, you'll be off by a constant, but you still.
What do you mean x to the 4th out of the cosine? I'm not sure what you mean by that.
Like, I don't know if I could pull the x to the 4th in the cosine of x to the 4th plus 1, if I could just turn that x to the 4th within there to the u, but I don't think so now that I think about it.
You said you're going to let u be the x to the 4th plus 1?
Yeah, because that would give you 4x to the 3rd for you.
Yeah, okay. So does anybody disagree with this? Cody sees x to the 4th plus 1. The derivative of that is what?
4x to the 3rd.
4x to the 3rd. Do you see that?
Yeah,
Kind
we're
of.
still off a constant.
Off by a
yeah.
constant. This will work. Okay, let's try it. We're going to do a different substitution. We're going to do u equals x to the 4th plus 1. The derivative of that is 4x cubed dx. And now that means I can replace everything in yellow, right? Gets replaced with u. And the green part, I need an x cubed dx, right? That's what I need. That's all I have here, an x cubed and a dx. I could slide that x cubed right here. You know what, I'll do it. Just so you can see it. I have cosine of x to the 4th plus 1 over square root of sine x to the 4th plus 1, and then times x cubed dx. I almost have x cubed dx. I'm still going to have to divide both sides by 4 here. But now I have a perfect match. This matches this. And then the yellow parts are going to be replaced with u's. So rewrite the integral. It'll be, the top is still cosine of u. The bottom is the square root of sine of u. And then the x cubed dx gets replaced with the 1/4, which I'm bringing to the outside, du. Y'all understand that? We're not done. We need to find the antiderivative of this, which we can't. This is not something easy. So we start over. Do you see something in its derivative?
Yeah, you got sine of u and then cosine
Sine of u. The derivative of that is
cosine
cosine of u du. Do you see that there? So I'm going to make another substitution, a second one. Now I'm not going to call it u because we already did u. I'm going to call it v. V is going to be sine of u. The derivative of v will be cosine of u du, not dx. So I'm doing the same thing I did here, but instead of using u, I'm using v because we have to, we already have u accounted for. Does everyone see that? There's something, there's its derivative. It matches. This matches. This matches. So now what I can do is rewrite it. 1/4 integral. Okay, the green part becomes what?
dv.
dv. I'm going to slap that to the outside. Okay, if that goes to the outside, I still have a 1 on top, and on the bottom I have square root of the yellow part, which is v.
Right.
And now that becomes integral v to the -1/2 dv. So just rewrite that, bring it up. And now at this point, power rule. Now we can do power rule. So this becomes 1/4 times, okay, v, I add 1 to the power, so 1/2, have to multiply by 2 over 1 on the outside plus c, which becomes 1/2 square root of v plus c. What's v?
Sine of u, and then
Sine of u.
and then
Okay,
we know
so
what
square
u
root
is.
of sine of u plus c. But what's u? You have to go back because we did 2 substitutions. U was x to the 4th plus 1. Same answer. Welcome to Cal 2. Okay, you ready for some more?
Just a random question about the integral thing. This is from my experience with your office hours of seeing the other Cal 2 students. There was always like a value on, or some kind of like either a variable or a number on the top and the bottom of the what's the thing called again? Of the integral sign. I don't know
Yeah.
if that's just like for domain for the more complicated problems or what.
Yeah, we'll get to that. Remember I said that this is called an indefinite integral?
Oh, okay. So it's without
Right.
things, and then
If
that
we
would be
put numbers here later on, that will be what's called a definite integral, and that's where it starts to deal with the area under a curve. Right now,
Okay.
this is just, hey, if I give you a function, can you find the antiderivative? Then later on, we say, well, what do we do with that? Like, what can we do with this antiderivative? Why is it important?
for this problem, we could just rewrite it x squared plus 1 to the 1/2 times x to the third, and then,
Well, hold on, Cody. I'm gonna ask somebody.
sorry.
That's all right. Brian, do you want a shot at this one?
Sure, why not?
How are you feeling about this right now?
A little wobbly. I'm not like super confident just yet, but
It takes time.
Sure.
It takes a lot of time and practice to get confident.
so I guess we can substitute, I guess.
Okay, so do you see something in its derivative?
Yeah, the bottom.
Okay, the bottom is the something?
Yeah.
Okay, so if you let that be the something,
Mhm.
what is its derivative?
Derivative of that is 2x or just 2x?
2x. Yeah.
Yeah.
So do you see a 2x?
No.
No. You see x cubed, right?
Yeah.
Actually, Brian, I'm sorry. This isn't really fair. I'm giving you a really hard problem. But
It's fine.
you'll still learn. You'll still learn.
Yeah.
So, but at least,
Um,
okay, you're doing the right thing. You're thinking x squared plus 1, derivative that's 2x, but we have x cubed, not 2x, right?
Yeah.
Okay,
Mhm.
so I'm not saying that's not the way to go, but let's just mentally go through this. Is there something else you could have chosen for your U substitution?
The top, the
The top,
numerator,
okay, x cubed. Now, what's the
Mhm.
derivative of that?
3x
3x squared. Now, do you see an x squared?
Yes.
Yes, but it's in the denominator
Numerator.
and it's trapped
has-
under a square root. So I told you no go on that, right?
Yeah.
So this looks like we might be stuck, doesn't it, everyone? I mean, it looks, we can't let u be x cubed because the derivative that's in the bottom. But Brian's initial idea was to do this, right? That was the initial idea. And that is actually correct. Now let's see why it's correct. If we do that, Brian, ready? We're going to let that x squared plus 1 go. The derivative of that you said is 2x dx, right? And we don't have a 2x dx. We have an x cubed. So Brian, don't get mad at me, but do you agree I could rewrite this problem this way?
To the negative or times x. Yeah.
I can do that, right? Algebraically, there's nothing wrong with that. That's the same problem, right?
Mhm.
But do you see now I have the x dx here and I have x dx here. I'm just off by 2, right? So let's scale both sides. Let's do 1/2 here. And that creates the x dx that we want, right? So this matches. You with me, Brian?
Yes.
So this right here will be replaced with 1/2 du. And this x squared plus 1 that you told me we wanted to be your u will be replaced with u, right?
Mhm.
The real question now, Brian, is what in the hell are you going to do with this then? Because if you make a substitution, everything has to get switched over to u's. You can't just have like some u's and also some x's. You have to replace x squared with something.
Yeah. Can't you do -1?
There you go.
Yeah.
So luckily for you, Brian, u minus 1 is x squared, right? This right here, if you take the 1 to the other side, you get this expression. So that means you can replace the x squared with u minus 1. That's awesome. Okay. Integral. Okay, Brian, tell me what we've got here.
So we got u
Replace
minus 1 on top.
U minus 1 on top over
The square root of u.
square root of u. Okay, and then what does all that green stuff turn into?
Turns into
the x dx turns into what? What is it equal to?
Oh, the 1/2 du.
1/2 du. Okay, so I'm going to put the 1/2 out here. And then I'm going to leave the du back here. Okay, so there we go. We're on our way. So do you all see, this is the first problem I've given you where the substitution that we made was not like clear. Like the substitution and its derivative, the derivative was not like glaring, like staring at us. It was, we had to like pop the x out and then we could see it, right?
Question.
Yes.
Could we have done it another way where we basically flipped the x squared plus 1 onto the top and set it as a negative 1/2 and then ran with, well, my something could be x squared plus 1 because it'll give, or no, my something could be x cubed and then, well, no, because then the derivative
still
wouldn't give me,
trapped.
yeah,
It's still trapped.
yeah, in the parentheses, and I wouldn't have the 1. Okay, never mind. I see now
Yeah.
why it wouldn't work.
Okay, good, Brian. I'm going to let you off the hook. Do y'all know what to do with this now? Gabriella, do you know what to do with that?
Again, your U and U.
I'm sorry?
I would say plug in the U and the U, but basically just did that but reversed it.
We need the antiderivative of this, right? We need to figure out what the antiderivative of this is. So we are either going to do another U-substitution, or we're going to maybe be able to do this with what we've already learned. So Gabriella, think about what we've already learned. What could you do with this that would make this problem a little easier to handle?
Could I maybe break it up to where it's
Yep.
1 over the square root U
Yes.
times?
You're going to do two. You're going to split this up like this. Now you can do this, Gabriella, right? You can do that because you have 2 terms on top and 1 on the bottom. You just can't do it when it's the other way around, right?
Right.
So now we can do this. Split it up into 2 fractions. I'm not doing the antiderivative yet. I'm just doing like, you know, just exponents here. So this should give me u to the half minus u to the negative half du. So that's u to the 1 over u to the 1/2. So you subtract the powers, you get u to the half, and then this is bring it up on top, you get that.
Right.
Now antiderivative, right? Now this is the time we can use power rule. So the 1/2 is going to come for the ride. And watch, because this 1/2 is in front of this and this is 2 terms, watch what I'm doing. I'm going to do 2 terms here and keep the 1/2 out front. So I need to add 1 to this. 1/2 plus 1 is 3/2, and I have to put the reciprocal out front. And then I add 1 to this power, so u to the negative 1/2 plus 1 is u to the positive 1/2. And I put the reciprocal out front, and there was a subtraction between them, plus c.
And then we just distribute the 1/2 and then be good. Is he talking for anybody else? I can't hear him if he is.
Yeah, I think his mic is messed up.
Yeah, your mic's messing up, sir. I'm seeing your mouth move. I guess everyone else is too, but nothing's coming out.
Try that. Yeah, I just saw a little alert that my audio was not good. Can you hear me now?
Mm-hmm.
Okay, I don't know what happened. Yeah, so now we distribute. Sorry, Gabrielle, I had to ask you if you were okay with this. Or
Oh, okay. I just heard nothing, so I was like, do I
yeah,
continue?
okay. You're okay with that?
Yes, I can. I was trying to follow along in the silence. Yeah, I can see the pieces connecting. I'm still a little fuzzy in vision, but getting there.
You understand I'm using the power rule, right? To
Yes,
get
because
from
you're just
okay.
adding one to
Adding one and then putting the reciprocal out front. Okay.
Yes.
Okay, so I've distributed through, I've got my powers here, and then U, I need to replace U, and U was, what was U?
X squared plus 1.
Yeah, hold on, my computer's acting really weird right now. Okay, so U was X squared plus 1, so X squared plus 1, X squared plus 1, and then all that plus C, and we are done.
Now, I guess I have another question about this. When we got to the 1/2 times the integral sign of u minus 1 over the square root of u times du, couldn't I have just flipped that u squared and then applied it to the u minus 1?
Yep.
And then it would have given, okay, it would have given the same.
You mean
okay.
like bring this up as a U to the negative 1/2, right?
Yeah.
And then distribute it through.
Right, which
And
give
you
me,
would have gotten to this point right here.
right, right.
Yep.
I just
Yep.
want to make sure I was allowed to do that in case we get into another scenario or
Yep,
something.
you can do that. Okay. So look, I could show you 1,000 problems, and then the next problem I show you would be different. So, I mean, this is really just a matter of you practicing. And that means you need to do problems from the book. So we're going to keep going. How about this one? I'll let you think about it for a few minutes.
Hmm.
Okay, who have we not heard from today? How about Daniela? I think your audio is kind of hard to hear, so try again. Do you have something?
So I'm thinking about like the x being the derivative because it's not like inside of something.
Okay.
Well, yeah, but like for the something, that's where I don't know, like it cannot be the x, right? Because then the derivative of that will be just 1.
So yeah, just a rule of thumb for everybody. When you're doing U-substitution, which we're doing right now, you will never let U be X. Okay, never. U will never be X, because if you do that, what will happen is you'll rewrite the whole problem. Like if I let U be X right now, du becomes just 1 dx. And so I replace that with U. I replace the X with U. And I replace the dx with du. So you basically get the same problem just written in terms of U.
You couldn't turn it into U minus 1 for the parentheses? Like we did in a similar problem? Or
Well,
no?
there's not a U, there's not a +1 here or anything,
Okay, fair enough.
right? It's just U is X, so it just gets directly substituted. So for U substitution, yeah, never let X. All right, so Daniela, what are you gonna do then? I mean, gotta do something.
Well, I can also use the power, right? But that will, like, I think that also will not help.
So we said U equals X, no, right? We're not doing that. U equals X, no. So do you have something else?
The 1.
Just
I mean,
one?
1 plus x.
1 plus X, okay. So what Daniela's just done is, I don't think Daniela has a clear idea that this is gonna work, right? I mean, right, it's not obvious whether or not that's gonna work, Daniela. But you're trying something, right? And that's what you have to do, you have to try something. So let's go with this, okay?
Okay.
So Daniela, if we do that, what's the derivative of this? So what's the derivative of 1 plus X?
Just 1 times
dx, right? 1 dx.
dx.
Okay, so Daniela, you're going to replace this 1 plus X with U, right? You're going to replace dx with du. So far, here's where you are. This is becoming U to the 90th, right? And this is becoming du. Are we good up to that point, Daniela?
Yeah.
Okay, what about the X plus 1 though? I mean, sorry, the X, what does that become? So look back over here. Is there anything you can do to get X in terms of U?
Something kind of similar, what Brian did, like move the 1.
Let's subtract 1 on both sides, right? Like that.
Yeah.
Okay.
Yeah.
So then that becomes U minus 1. Are y'all all on board with this? Good, Daniela. You're off the hook. Good job. So you have to do something though. So look at this problem. Can we do this now? How? How do we do this?
Distribute it out?
Distribute, that's it. Look, U to the 90th, multiply it through. U to the 90th right here. Just distribute it. We're gonna have U to the 91st power minus U to the 90th power du. Why didn't we do that to start the problem? Why didn't we do that in the very beginning? Why didn't we just distribute the X in? Because you can't. Order of operations says you have to expand this out first before you multiply the X through. So you're not allowed to distribute this X into this parentheses. But somehow, miraculously, with Daniela's substitution, we get a new algebraic expression that we can distribute through. And now that we can distribute it, we can just do power rule on each one of those. So this becomes 1 over 92, U to the 92, minus 1 over 91, u to the 91 plus c. And then we just replace u with what Daniela said it was, which was 1 plus x.
Yeah, I knew we were gonna do the u minus 1 somehow, but I did it on the wrong side.
Okay. We having fun yet?
Yeah, it's enjoyable. Challenging, confusing, worth it.
All right. Take a few minutes. We'll see, maybe Jesse next. Jesse or Samuel. Okay, batter up. Did y'all hear my sound effects? I was crumbling some paper and throwing it away. Did y'all hear that?
I think I heard it, but I was wondering what it was, but it didn't quite register. It's kind of just like
Yeah.
that presence in the background.
I just thought it would be sort of, a theme of try, start over, So Jesse or Samuel, did y'all get anything? Let me start with Jesse. Jesse, did you try anything?
To be honest, I'm kind of lost. The only thing that I could really think of was to rewrite secant cubed x as secant x cubed, because they're basically the same thing.
Yeah.
But that's pretty much as far as I got. I was just confused on where to go from there.
Okay. So when you think about choosing something in its derivative, like looking for something in its derivative, do you see anything here and its derivative? So let's start with like tangent, okay? You see tangent, right?
Mm-hmm.
What is the derivative of tangent?
Sine and cosine? Or
No,
sine.
what's the derivative of it?
Derivative?
Yeah,
I don't know. I think I forgot, to be honest.
okay. Okay, so that will be something you definitely want to fill those gaps because like I said, if you have trouble with that, it's going to be hard to see something, right?
Yes.
How about Samuel? How about well, let me ask you, Samuel, did you approach this? Had you gotten anywhere?
I did kind of the same.
Okay.
But I didn't get past this part.
Okay, so let me ask you, tangent. If that's your something, what's its derivative?
Secant squared, right?
Yep, secant squared x. Okay. Do you see secant squared x?
No, but
no,
kind of. I think
kind of. You could, if you wanted to, rewrite secant cubed as secant squared x times secant x, then your tangent x dx, right?
Mm-hmm.
And then you would have, if tangent is your u, the derivative of it is there, right? It would actually be that piece and that piece, wouldn't it?
Yes.
That might work. It's not going to, but I mean, just working through it, like that seems like that might be a way to go. Do you see that?
Yes.
Okay, so let's try it. Okay, let's see what happens. Okay. Jesse, does that make sense? Okay, so we're going to try this. U is going to be tangent x. The derivative of that is secant squared x, and then we tack on the dx. So if I rewrite the integral, I'm just going to rearrange things to make things look a little better. We have secant x, we have the tangent x, and then we're going to move that secant squared x dx to the outside, to the back side of this, so that we see the matching. This matches with this, and this matches with this. All right, sticking with you, Samuel, how could we rewrite this so far? The tangent gets replaced with what?
U.
U, okay. And then the secant squared x dx gets replaced with?
Du.
Du, okay. Now you have a problem. You have to get this secant x out of here. It's got to be something in terms of u. And the only thing you have is that tangent of x is u, right? Now you might say, okay, wait, I have secant squared here, right? So I could maybe take the square root on both sides, but you've also got a dx here. So if you were to try and do a square root, this right side would not be equal to secant x because you have a dx in here also. So you cannot algebraically try and manipulate that part in green. Your only hope is to try and get secant x out of this. Alejandro, what do you got?
Yeah, I just noticed something back on secant square x times secant x tangent dx.
Mm-hmm.
So we found out
What
that
did you notice?
Yes, I noticed that you plugged in secant square x dx for d of x, but we all know that's du equals secant square x d of x.
Wait, say again?
Yeah. Well, we found du, right, which equals secant square x d of x.
Yes,
So
Question.
then you plug that into d of x.
I plugged it into d of x. I'm not sure. No, I moved these two together. Like I just slid this one over here right next to this one.
Oh, okay, yeah.
This secant's here, this tangent's here, and then I grouped the two green ones together. So I didn't replace dx with this. Is that what you're saying?
Yeah, that's what I thought you did at first.
Okay, yeah, no, what I did is just move that green one over here, and that way it matched the derivative of this.
Okay.
So where we are right now is we're at a place where we cannot replace this easily with something in terms of u. Do y'all see that? We don't have a relationship. Cody, what do you want to say about this?
I was thinking, well, we could break the secant squared x into two secants, and then the derivative of secant x is secant x tan x. So then you could run with that.
So you're saying maybe we should just start with a different substitution then?
Yeah, I'm thinking, I'm just getting the feeling that this substitution may be doomed without multiple.
And the reason is
things.
this step right here. That's the reason why it's somewhat doomed. All right. But it's not all for naught. Let's go back up, and I want us to look at this line again. Okay, so this basically didn't work. So I want us to look at that line again. We had split it into secant squared x, secant x, tangent x, dx, right? That's where we were. We did that because we thought we were going to let u be tangent and then look for its derivative right there, secant squared. But do y'all see this is actually going to lead us to the correct u substitution? Does anyone see this?
Yeah.
What do you see?
Like, I'm thinking you have one secant, and then the derivative of that is secant x tan x. So you let the
Okay,
u.
stop right there. Cody just said that the secant x tangent x dx, Cody recognizes that as being the derivative of secant x. Right? That's the derivative of secant x. So this part in yellow without the squared could be our u. If we let the u be secant x instead, the derivative of that is secant x tangent x dx. And now look at how we can rewrite the integral. Secant x is u, right? So this becomes u squared, and everything in green is du. So it's just u squared du. And the antiderivative of that is 1/3 u cubed plus c. And that's just going to be 1/3 secant x cubed plus c. And that's it.
So I did pretty much, I mean, that's what I got. I just did it a little bit different.
How did you do it?
I might have done my algebra wrong, but I just made u equal secant 3 or to the cubed x, and then I took the derivative of that and got 3 secant squared x times secant tan x dx, and then that came.
Let me catch up with you. So you let u be secant cubed x. The derivative of that is 3 secant squared x times
secant x or secant x tan x times dx.
Okay, yes, that would be correct. But now you need to rewrite the original problem. So how would that original problem be rewritten?
Well, so from there, I got the 3 out and I made it 1/3 du, and then
Okay, so 1/3, get rid of the 3. Okay.
Yeah, and then I just combined. See, this is where I don't know if I did it right. I just combined secant squared x and secant x and made it secant cubed x tan x dx. So is that math correct?
You're right so far. Okay, now how are you going to rewrite the integral?
Sorry, my internet's really bad right now, so it freezes. I'm sorry, what'd you say?
How are you going to rewrite this then? You said, can I put those together? I said, absolutely, that's fine.
Yeah.
So how are you going to rewrite that then?
I just replaced it as 1/3 du.
So you're saying that this right here matches exactly what's right here.
Yes.
And so you're going to replace all of that with 1/3 du,
Yeah.
right?
Oh, wait. Yeah.
Yes.
Yes. I
Okay.
think.
What's the antiderivative of that?
I don't know.
No, yes, you do. There's a 1 right there. What's the antiderivative of 1 with respect to u?
What is it? 2, 1/2 or
Nope, you're trying too hard.
yeah.
Okay. What's the derivative of x?
1.
Okay, what's the antiderivative of 1 then?
What? I'm sorry.
You just told me that the derivative of x is 1, right?
Yeah.
So the antiderivative of 1 would be x.
Yeah. Sorry.
Okay, so this
Sorry, my computer keeps freezing, so I don't
I'm
like. I
being
get
real
like
smart.
bits and pieces. Yeah.
Okay, so what is the antiderivative of 1? But be careful, the variable's u here. So the antiderivative of 1 would be
Du
just u,
or just okay. Yeah.
right? So this would be 1/3 u plus a constant. What do y'all think? Is this right?
I feel like it works
What
because
was
you
u
replace
for,
your u.
for Bree? U was secant cubed, wasn't it?
Yep.
Same answer.
Okay. Great.
So here's what I'll say. I mean, I've been doing this for a long time. Okay. I've been doing Cal 2, like teaching Cal 2 for 20 years, and I've been doing Cal 2 for a lot longer than that. I don't think I've ever seen someone do it that way. In fact, I know I've not seen anyone do it that way.
Breathe the innovator.
Now here's the thing. I think what happened is you actually stumbled upon the answer. Like you tried something and it worked. You didn't break any rules. You did everything right. So the thing I would say is you tried something, it worked, but what you tried initially should not have been something that
would work every time.
If you let this be your u, you should already at that point be like, well, wait a minute, the derivative of that is definitely not tangent, right? So if you're saying this is your something, the derivative of that is not this. So most of the time that would turn people away from doing that substitution. But you just did it and just said, I'm going to go with it. And it turned out that this right here actually matched perfectly with the whole expression. So it worked. Now it won't always be that way. Just for this problem, it worked. So good job.
Oh, thanks.
I don't think that a lot of people would follow that path because it doesn't seem very promising, but it actually works.
Yeah, I'll give her credit. I wouldn't have done it. I thought she was off the rocker for at first at the beginning. I won't even lie to you.
Well,
But-
I just
All right. So look, I mean, I hope what you're getting from this is a feel, a taste for what this is. I mean, there's this debate, like Cal 2 and integration and learning all this stuff. And people will say, well, you can just go to what's our favorite symbol lab or something like that. And you can just go in here and you can say, all right, well, let me find the antiderivative of, I don't know, should we try that one? Secant, what was it? Secant x. What was it?
X to the third tan x.
Right, oh shit. Raised to the third times tan x. See if it takes that. See if I typed it in right. There it is. There's the answer. 1/3 secant cubed x plus c. Okay. So people will sit here and be like, well, why are we doing this? Like, there you go. You have the computer. And I agree. We have the computer. And if you were building me a bridge that I'm going to drive on, I want you on the computer. I don't trust you. Okay. And engineers will use computers to solve complicated integrals. This has very little to do with that, though. This is about a way of thinking. This is about using parts of your brain that are useful for when you're sitting there and you're the engineer and you're trying to solve the big problem, right? When you're, it's training your brain to think a certain way. I hope that what you're seeing is that this is a different way of thinking. This is not Cal 1 stuff. This is not that mechanical process. This is a higher level thinking. And so as you progress through Cal 2, you start to push your brain to a certain place. I don't ever want to see that get replaced with, we're just going to have computers do that, because then you never get that training of your brain to think a certain way. You're not a problem solver, right? So, all right. How are we doing on time? We still have time. All right. How much more of this do we want to do before we say, all right, that's enough. It's time for you. I have another challenging one. All right. I'll give you some time.
Ooh. Hmm.
I'm going to open the floor to let y'all talk for a few minutes if anyone wants to kind of bounce any ideas off each other.
I'm thinking maybe a half angle formula transformation, because the cosine squared of x is going to give you 1 plus cosine of 2x over 2. And if you use u equals sine of 2x, then you'd get d of u is equal to 2 cosine of 2x. And if you clear the 2 without the bottom of your denominator, the fraction out of your denominator, you'd get 2 plus 2 cosine of 2x. So then you'd have your something, and then you'd have the derivative of your something. Well, no, but hold on, the derivative's in the bottom. Damn, never mind. Unless we flipped it first. Anybody think that's wrong, right? Any other ideas?
Yeah, I thought the U was pretty right in that sense with the sine 2x.
I guess maybe you flip the 1 plus cosine squared x first, and then you could turn it into that. But then you'd have, I don't know. Yeah, I feel like it's the right approach, but I feel like I'm missing the application. Thinking it could be the wrong approach, so.
Hey, I had stepped away, so I don't know what y'all were talking about. Does anybody have it?
I'm thinking a half angle transformation, but I'm not sure because I think it would leave it in the derivative in the bottom, which would be bad. So if you could flip it, maybe then. But I'm not really getting much
Do y'all
feedback
want-
from the others.
y'all
So
want a
I don't
hint?
know.
Y'all want a hint?
Mm-hmm.
Is there a way you can rewrite this from pre-cal?
The 2 sine x cosine x. And then we got our something in the top then. Bottom.
Jair, is that, do you see it? Is that why you did that?
Yeah, because couldn't U be cosine squared x? And because the derivative of that would have the 2 sine x cosine x?
Yeah. Yeah. You know what? Grab a little more.
Oh, the 1 plus cosine.
Ah, there you go. Look, 1 plus cosine squared x is the U. Now, why? Because if you take the derivative of this, the 1 goes away. Derivative of cosine squared x is chain rule. So 2 cosine of x to the first power times derivative of cosine, which is negative sine of x, and then you have your dx. And I think Jair was saying that's what you were seeing, right? That this 2 cosine x negative sine x, that's kind of what you have on top.
Yeah.
You're off by a sign though, right? You have 2 sine x cosine x dx, 2 cosine x sine x dx, but the negative. So that's okay. We just multiply both sides by -1. So negative du is 2. I'll rewrite it in the proper order. And now it matches this, matches this, and this is that. The only other way you would have got that, I mean, well, you would need to do this double angle identity. But if you didn't see all this, the only way you would have got is just to try it. I mean, you would have had to like, let me try U as 1 plus x cosine x squared, you know, like that's the only way that you would have known is just to take a swing. All right, so we rewrite the integral. We have the yellow part on the bottom, that's going to be U, so that just becomes 1 over U. And all of the green stuff becomes a negative du. So I'm going to put a negative on the outside, du. What's the antiderivative of this? 1 over U. That's that special case, isn't it? Negative. Antiderivative 1 over U. Natural log, absolute value of U plus C. And then replace U with what it is, which is 1 plus cosine squared x plus c. And we're there.
If they were flipped, could we have done it the way I was trying to at the beginning where you did like sine of 2x and you just let that be your u? And then you take the derivative of that and then you get.
If
Well,
they
no,
were
'cause-
flipped, what do you mean they were flipped?
Well, if they were flipped and I turned the cosine squared of x into 1 plus cosine of 2x over 2 on the top, all over sine of 2x. Sine of 2x is my something. I clear the fraction first on the top,
Oh,
so then,
you're saying if the original problem
right,
would have been the reciprocal of that, like
Mhm.
this,
yep.
then, and then you do what?
I really don't know if I could do it, but trying to use like one of the half angle formulas, like I know cosine squared of x is equal to 1 plus cosine of 2x over 2. But I don't know if I can do that with this since it's an expression and not by itself, actually.
Yeah, that, you could probably do that.
Then I would divide out the 2 or multiply 2 out and then to clear the fraction on the top and you get 2 or no, you wouldn't. I don't think it would work. I think my mental is not adding up right. Never mind.
Yeah, I mean,
Alright.
I think it would go. I mean, I think it would go. I would still do the double angle. I'd still turn this into 2 sine x cosine x, and then
Right.
just split it into 2 fractions.
Yeah,
But, yeah.
yeah,
Okay.
that method I was saying was wrong.
409, 410. All right. One more. Last one. I'll give you a minute, couple of minutes.
I figure you'll know while I'm waiting for you to break this down a little bit. Was it Albert Einstein or Thomas Edison that had problems in like early elementary math because he was not interested? I don't remember.
I'm not sure.
Okay, fair play.
All right. Well, anybody have any luck with this? So I put two quotes up here. The first one I think is funny because it kind of, that's just kind of the way math works, right? Like when you get to Cal 2 and you start doing the work in Cal 2, you're like, man, I wish I was back in Cal 1. You know, so like students that are in Cal 1, they're like, man, this stuff is, you know, rough. And you're like, yeah, wait, you know, it gets worse, right? So math is just like that. And then the other one is a quote that first time I saw that was at my daughter's gymnastics place that she used to do gymnastics, and they have that on the wall. I don't know if anyone like has like who said it, whose quote that is, but I like that quote. That's a really good quote for Cal 2. You know, it's not a matter of you just doing a problem and getting it right. You want to get to a point where, given any problem, you have that confidence that you're not going to get it wrong. You know, there's two different, that's a different levels of understanding, right? Okay, so let's see. Did anyone just, even if it didn't work, does someone want to share something that they tried?
I guess I'll go. So I tried splitting up the bottom x to the 6th as like 2x cubes. I don't even know if that works.
Oh, I did that too.
I was
Okay.
just going with it. And
Wait,
then
you split it into what?
I did 2x cubed.
Why did you
but
do
I don't
2?
think that's right.
You
Wait,
did like
you mean 2x cubes multiplied together?
Yeah.
Oh, okay, like this.
Yeah.
1 plus
1
x
plus
cubed times x cubed, right?
So can I
Yeah,
ask
that's
you
what I did.
why you did that?
So I could have an x cubed on the bottom, and then I saw the x squared on top, which is
Okay,
like,
so this is almost like, Christian is almost like in Brie, I think the same thing, is almost like trying to like reverse engineer it. Is looking at the 5x squared going, God, I wish I had an x cubed. Because if I have an x cubed, then the derivative of it, 5x squared, is up there, but it's off, right? It's off by a constant. That's okay. So in your attempt to re-engineer it, you wanted to rewrite x to the 6 as x cubed times x cubed. May I suggest a different way? X cubed squared,
that works too.
right? Good, that's gonna work.
I wish I thought of that before I went halfway through it.
No, that's gonna work. I mean, but you still should have got it the other way too. So you make your substitution. U is x cubed. The derivative of that is 3x squared dx. Oh, I forgot my dx here, sorry, dx there. So let me rewrite the integral first. The 5 is just in my way, so I'm bringing it out. I have 1 over 1 plus x cubed squared, and then I have x squared dx. I'm sliding the x squared to the back. I really need this x squared dx to match, so I don't like the 3 here. I'll just multiply both sides by 1/3. Now it matches exactly.
I did it slightly different. I just did.
I'm not surprised.
I just multiplied both sides by 5/3, so I
That's
could
what I
get
did.
5x squared dx.
Oh, yeah, you could do that too.
Okay, yeah.
Yeah, yeah. Okay, so what Bree did is said, I really want a 5x squared dx. So multiply both sides by 5/3. That'll kill the 3 and create the 5, and that works fine. Very good. Yeah. Either way, me personally, I just have a habit of just always, if the constant's not helping me, I'm just going to pull it out. I'm just going to get it out of my way. But it works the same. All right, so here we go. We should be able to rewrite the problem. It should be 5 integral 1 over 1 plus what?
U squared.
U squared. Du. Sorry, there's a 1/3. I need that 1/3 to come out. Let me bring the 1/3 out with the 5. So that 1/3 comes from that 1/3 right there. So now we're at 5/3. And then do you all recognize this? 1 over 1 plus u squared. That's the important one, right?
Is that the inverse of tangent?
Inverse tangent, in this case of u plus c. And now we replace the u with x cubed. There it is.
I didn't even think to do that transformation at the beginning. X cubed squared.
I think the key to making that substitution is, again, the idea that you have a 5x squared and you'd really love to see an x cubed.
Yeah.
That's where that comes from.
Yeah, I guess just realizing, looking to make similar exponent or similar exponential values.
Yeah. So what we've done in the class today, is I've, shown you this general strategy of U-substitution and given you some various kind of approaches and problems where you have to try different things. It's now really up to you to go and do the homework and practice problems. And my advice to you would be, as you prepare for Cal 2, that this section 5.5, so we've actually jumped all the way to 5.5. My recommendation for the homework, there is no homework here for 5.5. No, I didn't give you homework. Okay, so I'm going to tell you what the homework I think you should do is from 5.5.
Wait, is this, I thought we just did 5.5.
Well, there it is. It's page 306 in the book. 1 through 36 all. Page 306, 1 through 36 all. That's my recommendation. I mean, there's no such thing as doing too many U-substitution problems. And if you're doing a problem in the book and you see in the problem that they have the integral sign and a number right here and a number right here, ignore the numbers and just forget they're there and just go find the antiderivative. If you do that, though, keep in mind that your answer will not be the same as the answer in the solution manual because they're doing something else. It's kind of weird. The way the book does this is they teach you definite integrals before they get to use substitution. The way that I do it is we say, here's antiderivatives, here's U-substitution. And then after we do all the 5 techniques, then we go do the definite ones. So, yeah.
So when we started the U-substitution, that was a different section. That was 5.5?
That was 5.5, yeah.
Oh, I thought that was the second half of the antiderivative.
No, the
section
second half
4.7.
of the antiderivatives was what we did earlier when I was showing you if you start with
okay, so velocity.
F double prime and going backwards.
Okay.
Yeah, that's the second half of 4.7, I think.
Okay, I was wondering why
I should have clarified that. When I put this up here, I don't think I showed that it was 5.5.
You might have. I might not have been paying attention, sir. That's probably completely possible. It's my error.
Yeah. So, what's our plan? Our plan now is I'm going to try and get you all a review for the final. And hopefully I can get that out in the next day. And then when we come back on Tuesday, I am going to talk a little bit about definite integrals, just so you can see. I think we already started talking about how you can use this to get areas under curves. Just give you a real brief introduction on that, maybe spend an hour on that. And then the rest of the class, I think we'll probably spend on just talking about the review. If there's something on the review you want me to go over, any other questions you might have. So, yeah, I mean, we've gotten as far as I want to go, other than what I want to show you on Tuesday. So I think we're in good shape. Any questions?
Anybody taking Cal 2 in the fall? I'm sad. This class is already ending, and I just got used to seeing all of you guys. Well, most of you people.
I'm taking Professor Di Giovanni for Cal 2 next
Are you
semester.
doing the face-to-face one?
Yeah.
Okay. Yeah, I'm so
taking the
excited
same
about
class.
Me too.
that. Yeah.
That's
Same
so
here, I'm
exciting.
gonna take the face-to-face as well.
Yeah, it filled up pretty fast.
Yeah, they capped it at 10 people, and then when they went to the next level, they opened it up to 15, and it was filled up pretty quick. So
I got it on the next level.
on the
I didn't.
15,
It's the one that's at 9, right, sir?
What's
9 in
that?
the morning? It's the one that's at 9 in the morning, right?
Yeah.
is it really?
It's
Yeah.
I
early,
think
yeah.
so. Yeah.
You guys are lucky. It's
Yeah,
I
who
could.
does
I didn't
that?
even see him when I signed up. I do like through the
Yeah,
military and
Cruz is the
stuff.
one who let me know.
Yeah, I
I
do
had to
mine
pull
through the
strings at
military.
my
and stuff.
job just to get
Because
that
it was
class.
capped, I was like,
No.
because it was capped, I was like, well, I guess I'm gonna have to do a different professor. And then I looked back like the next day, and I was like, wait a minute, did people drop?
Yeah,
Were
they
you
opened it up.
Were
And
you
they
scheduled?
might, I don't think they're going to, they might open it more again. I don't know.
Were you scheduled earlier in the year to teach an in-person class? Because I had to sign up really early for the military stuff, so I didn't actually even see you. I hadn't even taken your class when I signed up. Otherwise, I would have looked for you. Rip.
Well, I haven't been on campus. I've not been to my office since spring break of 2020, right?
Yeah.
So I've not sat in my office.
You said, even though I'm with a different teacher, you said I could still pop into your room and talk, ask questions, right?
Yeah.
Because I don't know. I don't like to change professors when I find I like this professor's explanation method and all that jazz, and I go to somebody else and it's like, oh shit.
Yeah, I understand that. My only kind of response to that would be the further you get along in your academic pursuits, right?
Mhm.
You're not
Yep.
gonna be able to like handpick who you get. Like, and sometimes you get the one that everyone tells you don't take because that they're the only one offering that semester,
Yeah,
So
well,
part of it is somehow finding a way to grind through regardless of the instruction,
right. Well, then I talked to my aunt about it. She's a big CEO for Helen and Troy, I think it is, but she said it's also good to get different professors like that because it exposes you to a broader, type of thinking in a sense. Cause like what your method may be different from the others to an extent. So something like that,
Yeah, I've had students take me for Cal 2 and they've had to take it 3 times just because it's Cal 2. And I always tell them, like, after the second time, I'm like, you might just try somebody else. I mean, not that I don't want you here, but like, maybe you just need to see it a different way. I've always taught math the way that it makes sense to me. And that doesn't always necessarily make sense to other people. Sometimes people have other ways of thinking about it that makes sense to them, but to me, it doesn't make sense that way. So it could be that, just the way people's brains work, I'm kind of this philosophy at the calculus level. I don't look at any of my students as being like pure math, like math major, pure, like, what am I trying to say? Okay, how do I say this in a
we're not far enough along for you to treat us as, pure from a pure mathematical standpoint.
Let me say it this way. I've told you all my story, right? About how I
Mhm.
struggled with math and I got my shit together and everything. So if I would have had a Cal 2 professor who was just trying to grind us down to nothing and expected this super high level from us, then that's where it would have ended for me. You know, I was not, I believe you can still reach very, very high without having to be like a perfect math student in Cal 2. Like you still have a lot to learn about yourself and the way you learn and discipline and dedication. There's still a lot of room for growth there. So I never expect my Cal 2 students to be like just perfect Cal 2 students. Like, you know everything, I'm gonna give you the hardest problems, you know. No, it's a buildup. So when I teach it, I present it in that, I try and present it in a manner of like, look, this just needs to make sense to you. You may still struggle with it, but it needs to make sense to you, right? Like it can't just be, I don't know, I'm not making any sense, but whatever. Variety is good sometimes. So we'll see what happens.
Yeah, I guess I'm just worried that I'm gonna get like the opposite of you, which is gonna be more like a much more focus on mechanics and then difficulty level, etc.
Well,
Not to say your class is easy or anything, but it's more of you build it up to where opposite would be something like, I don't know how you treat Cal 3 students, but maybe in Cal 3 you assume that they're on top of their shit at that point. So then you start making it harder. I don't know.
no. I pretty much treat all the calculus pretty much the same. I mean, your expectations get higher. Like I do expect that you look at something in Cal 2 and you can take the derivative of it in your head and not sit there and struggle with it. But as far as like, I still look at this as, I guess this is why I do this, is I actually enjoy watching students discover this subject. Like it's very enjoyable to see people's like, I get, you're like, oh, I see it, you know, like that feeling you get when you solve a math problem, right? When you like get it, you're like, oh my gosh, you get that feeling, right? I enjoy helping students get to that point where they can enjoy it, you know, and like get that pleasure from it. So in all calculus, I treat it the same way. It's like, I get excited about it. U-substitution is exciting. It's a different way of thinking. It's challenging, but it's fun. It's a puzzle, right? You're trying to figure this shit out. Oh, sorry, Brady. Got the minors in the session.
He has no idea what any of that.
Yeah, y'all are free to go. Y'all don't have to hang out, but.
So then in your opinion, when would it reach a point at like what math level would it reach a point where you're no longer as lenient? It's more about, you know, you would have a higher expectation of that.
I'm not going to say leniency. It's not leniency. It's just a matter of like, when you're in calculus, you're still, there's a lot of different things you could be doing with math, right? So I think for math specifically, for me, it gets really serious when you get to your theorem proving courses, which starts with a course called Foundations of Math. And that's when the professors are not going to help you, okay? They present the material, they give you the theory, and then it's up to you to figure it out. And you can't go to a tutor for help. You can't, you know, it's just like, now it's a matter of, does your brain think this way or not? So I think for math people, that's where it happens.
Okay.
Before that though, I think it's all about discovery, you know, it should be all about discovery.
I had asked you at the beginning of the semester, but I don't really remember your response, but do you know what discrete mathematics is? Because I have to take that after Cal 2 and I have no idea.
It's like a cornucopia of math concepts that are somewhat connected and disconnected. They're just it's kind of all over the place. Discrete means like finite, right? Like discrete, finite.
So all the odds and ends essentially.
Yeah, I mean, if you look up a syllabus on discrete math, there's a ton of stuff on there. Yeah, and so it can vary from school to school depending on what they want to focus on. But
do you teach discrete mathematics at Northwest Vista?
We don't offer discrete math at Northwest Vista, or I don't think I'm not sure if any of the Alamo colleges offer it.
I think you guys do, because I'm supposed to take it, and my advisor didn't tell me that it wasn't at the stuff. I'm scheduled for my plan to take it in, I think, 22.
We've never offered it at Northwest Vista.
All right, well, hopefully I don't have to dodge that hole later in
Yeah.
life.
Yeah.
Shit.
Yeah. All right, well, anything else?
No, sir, I guess I'll see you.
Enjoy your
next
homework.
week.
Enjoy 5.5. All right, y'all have a good one.
Do you have
Sure.
videos over 5.5?
Oh yeah, you know what? Let me look here. Good
I
question.
believe it is, actually. I remember
Or would
seeing
it
it.
be like Cal 2 or something like
But
that?
I don't know if it's in the Cal one. Let me see. I think I've added it to both playlists. Let me see. For the solutions for the homework.
Yeah, it's there.
A phone plan
24:14.
Yeah, it's there.
It's easy to switch to 5.
It's
from the
only 2
comfort of
hours
your
long.
home. Purchase a phone or use the phone you have.
What are you? Okay.
So this will be equal to, let's see. I'm wondering, I'm wondering if I do them all. Or if I skip. 29, 28, 26. I think I do them all.
Keep in mind that
Looks like I've got a lot of.
let me get,
Yeah, I think I go through most of them.
let's see, it's cubed up there. Can't peel.
But
it
you
out.
have to keep in mind that when I do it, I'm not doing it like we did here, where I'm like, oh, think about it. Okay, let's go down this road. It's like, I already know the road. Let's go. You know, so when you do the homework yourself, you want to have already tried several things before you come here. Worst thing you can do is just sit here and watch me and go like, yeah, I could do that. You know, because that's, you're not getting that part going where you're figuring it out. So
Yeah, I usually use them as just like a guide, to make sure I'm going the right way.
yeah,
Check my answer, and if it's not wrong, then or if it's wrong, then I'll look where I went wrong and then try to fix that and then go from there. Pretty much what we do in the office hours, except you don't respond to me. I just watch the video.
yeah. And the good news, I mean, like for those of you who might be taking me in the fall face to face, is that I'm going to start in 5.5. So I'm going to redo U-substitution. I'm going to start from scratch because not everybody's going to come in having done it. So I'll do that. But the thing is, with the 5 methods, right, the U-substitution is the easiest one. Okay, so you can't do any of the others without U-substitution. So like what will happen is when we get to a later method, we'll do a problem and then we'll be using some other method, let's say integration by parts. And then within that problem, you will reduce it down to a U-substitution problem. And so you'll have to do the U-substitution to finish it. And then later on, the next technique, you realize, oh crap, to do this problem, I've got to be able to do the integration by parts, but then that's going to require the substitution. So you can't have any holes at this point with the integration because everything is going to build on itself. And then the hardest thing, in my opinion, the hardest thing is when you get to the test. Because when you get to the test and you're presented with a problem, you're not told what to do. Like right now, if I gave you a test, you know it's either going to be like a formula that you've learned, like, you know, power rule, something from Cal 1 or U-substitution. That's it, right? That's the only thing that it could be. But in Cal 2, when you get to that first big exam, it can be any of these 5 things, right? So when you look at the problem, you're like, okay, is that U-substitution? Is this integration by parts? Is this trigonometric substitution? Is this, you know, and so that is going to come with the practice. If you don't have the practice part of it, then you'll sit there looking at it, you'll go down the wrong road, and 15 minutes later, 20 minutes later, you'll realize that's the wrong way. So that to me is the hardest part of this aspect of Cal 2. So
It would be a
anyway,
tough summer course.
one foot in front of the other. Jair, what?
But like ultimately at the very end, you could kind of check yourself if you're correct by taking the derivative, right?
Yeah, I've seen a few of the Cal 2 things he does. I don't know if it would work for every scenario.
Well, you can always check. You can always check, but let me just show you here an example of an answer from a Cal 2 problem. Okay.
Coming back, antiderivative of 1 with respect to theta. Theta, which is
Let's see.
sine theta,
Here we go.
and then answer is theta.
So, trying to get to the answer. Oh, there we go. There's an answer. So do you really feel like taking the derivative of this, right? Like this is derivative of an inverse sine function. You got some chain rule in there. This would be a product rule because you have x times this. So that, you know, so could you theoretically check your answer? Absolutely. But will you have time during a test to do that? Probably not. So you're going to just have to trust that what you did is right. And what I'm not looking, like when I grade things, I don't look for like perfection. I'm looking for proper approach, right? Are you using the right technique? Are you following the steps? Oh shit, you messed up a sign there, but is everything else right after that? You know, like, do you carry on with that mistake correctly? That's the type of thing I'm looking for, because we're all human, we're going to make mistakes, but it's the bigger picture, right? Can you put it all together and organize your thoughts? And you see, this is the last section here.
Now,
Partial fractions. Yeah.
but because this is a form, we get lucky. The square root of x is actually used.
Okay, so here's a problem. I'm doing a basic U substitution.
It's a long time for the beginning.
Okay, this is a basic U substitution problem. But when you do the U substitution, after you do the U substitution, it turns into a different type of problem that's not possible to do unless you do this thing called partial fraction decomposition. And yeah, so again, it builds on itself.
That reminds me of something. Will we ever have like an integral that uses U substitution where we would have to factor it all? Or would that not really work out that way?
Yeah. Yeah.
Okay.
Like complete, you could get a quadratic where you complete the square. And then the part that is squared could be your U substitution.
Okay.
Yeah, there's a lot. I mean, there's a lot of things that can happen. So, all right.
I had a question about one of the previous problems we did with like 6 when we were doing I guess the 6th one, the one that we had the integral of secant cubed x tan x dx.
That one.
Yes. Okay, so I was wondering, like, I don't know if it would actually get us to that answer, because originally I did do it like redid it, but I crossed it out because I didn't do it as fast as she did, and I thought it was wrong.
Okay.
But when you started off and you did it the initial way where we had, I think, tan BRU.
Yeah, right here. Mm-hmm.
Yeah. With that secant squared x, with the tan, or like that secant x,
Yeah.
tan x.
Mm-hmm.
Would you be able to substitute that with the 1 plus tan, or I think it's 1? Is it 1 plus tan for like the
Oh yeah, the Pythagorean identity.
Yes.
Yes, you could replace this secant squared right here with 1 plus tan squared x. So I think what maybe you're saying this, could you have taken this and rewritten this as tan squared x plus 1 times secant x times tangent x dx? Am I correct?
Yes.
Like do that? Yes, you could.
Okay.
The question would become, then what? Because at this point, what are you going to do with it? Like, are you still going to let u be tan? If you do, then the derivative of this is secant squared. You no longer have secant squared here,
Mm-hmm.
right? So algebraically, you could do that, just it may not get you anywhere.
Okay.
Yeah. So.
Oh, if I end up doing the work for that half angle formula that I was thinking for that one problem, can I shoot you the work? Can you tell me if it's right? It's probably gonna be like 2-3 pages. I think it's gonna be long and clear everything, but
This one?
Yeah, if I do that and I turn that cosine squared x into the half angle formula and run from there.
Are you saying, well, I can't say yes yet because I don't know if it'll work. In the big picture of things, not everything can be integrated. Okay, so like we can't always find the antiderivative of everything. We have to be real careful how we choose things. So that, like that, right?
Right, and then I guess I'd let my something be the sine of 2x. Actually, no, I don't think it works when you FOIL it out.
The problem you're going to run into is, let's see, this is a half, that will become 3/2 plus 1/2 cosine 2x, then over sine 2x.
Yeah, it wouldn't work.
Over sine 2x. This turns into cotangent. And the antiderivative of cotangent is not something we've learned yet.
Yeah, I did a bunch of like mental math when we were discussing it, and I thought it would work, but it doesn't. So.
But I mean, you know what? I'm looking at you. You could do this. This one, maybe not. This one for sure, yes. Because this could just be a basic U-sub. U is sine 2x. The derivative is up here. You're off by a constant, but it's okay.
Yeah, it's that +1 that's throwing me off. I think if it was just cosine squared of x on the bottom, I could, or cosine squared of x on the top, I could probably do that.
Yeah.
Is that okay? Good enough.
All right, everyone.
See you next
Have a
week,
good
sir.
one.